Hi, welcome to the Advanced Bitcoin Blockchain course by Cody's Alert. This course is designed and developed by our instructor Anni, who is a certified blockchain and Bitcoin expert with 11 years of experience in the banking and investment industry. In this course, you will learn and implement advanced Python concepts, all the core Bitcoin concepts, building a fully functional blockchain from scratch, and creating Blockchain Explorer with HTML and CSS. At the end of this course, you will have a fully developed functional blockchain project that you can add in your portfolio or use as a foundation for your next blockchain product. This course is designed for both beginners and advanced learners who are keen in understanding and developing blockchain concepts. If you have any questions regarding any topic, feel free to post in the Q&A page and we will help you clarify it. Do leave your feedback after the course completion as your feedback matters to us. Wishing you good luck.
Hey guys, welcome to the Advanced Blockchain course. My name is Anni. To start this course, we need to install a couple of things. So first we need to install Python. So let's go to the python.org. Go to downloads. Download the latest version of Python. Click on the setup file. Click on add Python to the path and install now. So while this installation is in progress, let's start downloading the Visual Code. Click on the download. It will automatically start the download. It has started the download. You can setup is still in progress. Let's wait for it to finish. Okay, so setup is successful. You can close this window. Let's go back to our Visual Studio setup. Okay, so we have the Visual Studio setup file. You can click on accept the agreement, create desktop icon, yes, install. And for now, we just need the Python and the Visual Studio editor to start our coding. Let's wait for it to finish. Okay, so Visual Studio setup is completed. You can close the browser. Now that we have the Visual Studio available, go to File, Open Folder, go to Desktop, create a folder named Bitcoin. Okay, so the next thing that we need to do is we need to create the virtual environment. It is a best practice when you are working in Python to create the virtual environment for large projects. So open the terminal, type python -m venv and the virtual environment name. So I'll give venv only. So you can see here under the Bitcoin folder, it has created the virtual environment here. So in the next step, we need to go to settings. Click on settings here. Click on this button. It will open up settings.python file. We need to set the Python path. Whenever we open the terminal, it should automatically activate the virtual environment. So let's do that. Python.python path. Copy this path from here. Change the single slashes to double slash. under Bitcoin, we need to get inside VENV or virtual environment name and scripts. Save it and close this now. Delete the terminal. Now create a demo.py here. Open up terminal now. As you can see, it has automatically activated the virtual environment. In the next step, we need to install the dependencies that we need for this project. So let me copy the requirements.txt file in Bitcoin folder. You will find this file in the attached page. You can download it from there. Copy this file to Bitcoin folder, desktop, Bitcoin, copy here to pip install -r requirements.txt, enter. Now it will install all the libraries or the dependencies that we need for this project. It will take a couple of minutes to finish. So once it is done, then we will start our tutorial. Let's create a quick version of our blockchain. Before we do that, let's define the project structure. Inside the Bitcoin directory, go ahead and create a new directory called blockchain. Inside blockchain, create another directory called backend. Head back to blockchain, create another directory called frontend. Head back to backend, create another directory called core. Inside this directory, all our Bitcoin or blockchain core modules will reside. Now let's go ahead and create a new module called block.py. Create class block. Let's add a description for our class. So block is a storage container that stores transactions in our case, but you can store anything in block. Since we are designing a cryptocurrency, so transactions are the valid data to store. Block is a storage container. Let's define the init method. Block class takes height as an input, block size as an input, block header, transaction count, and transaction itself. Height is the height of block, size is the size of the block. Block header is comprised of various fields that we'll see it shortly once we'll create the block header class. Transaction count is the number of transactions, and this is the transactions itself. Let's head back to the core module and create a new module called block header. Create class called block header. Define init method. Block header class takes version as an input. So this is the version of your blockchain. Previous block hash. So this is the hash of your previous block. Merkle root. Don't worry about Merkle root if you don't know what it is. Timestamp is the timestamp of your blocks when it was created, and bits is the target difficulty. Don't worry about bits if you don't know it. In the subsequent videos, you'll understand. So let's go ahead and define it. All right. So inside the block header class, we need to create another function called mine. Mine function is used to mine the block. So let's go ahead and define mine function here. Before we create the mine function, we need to create another directory called util. Inside the util directory, create another module called util.py. So this holds all the utility packages in the util. Go ahead and import hashlib. For mine function, we need to create hash 256. Let's go ahead and create this function. So what is hash 256? Hash 256 is the 2 rounds of SHA-256. So basically, first it will create the hash and then it will hash that hash to create a new hash. So 2 rounds of SHA-256. Define hash 256. It takes string as an input. Let's add a description. 2 rounds of SHA-256. Return hashlib dot SHA-256 string as an input and then digest. So it will spit out the hash in byte format. Since we are doing the double hash, so let's do one more round of hashing and digest. Alright, so we are done with this. So let's make a util directory as a package. So for that, we need to create the empty init.py file. Now we should be able to import this wherever we want. Let's go back to block header class. Import hash 256 from blockchain dot backend dot util import hash 256. Let's go ahead and code our mine function. So before we do that, so we also added two fields here, nonce. Nonce we set it to 0. We added the block hash to blank. Block hash has first 4 leading zeros or not. So how to create the block hash? In order to create the block hash, we have to concatenate all these fields together and then we have to pass these fields as an input to the hash 256. It will generate a hash and that hash will check if it has the leading zeros or not. Let's go ahead and code that. Self dot block hash 256. In order to concatenate all the fields together, all the fields should be string. So any field that is not a string, we need to convert it into a string. For example, the version field is a numeric field, timestamp is a numeric, nonce is a numeric. We have to convert all those fields into a string field. Let's go ahead and do that. Self dot version plus self dot previous block self dot Merkle root timestamp convert it to string self dot timestamp split it to the next line self dot bits plus string self dot nonce. Now we need to encode all these fields together. before passing it to the hash function. Let's encode dot encode, and this hash function returns the result in a byte format, and we need to convert it into the hexadecimal. Let's go ahead and do that. Convert it to the hex, and now we have the block hash. So block hash is calculated by combining all these fields together, and the only thing that we can change to generate a different hash is change the nonce value. So let's increment the nonce value here. Self dot nonce 1. Alright, so let's understand what exactly we did. So once we'll call the mine function, so we know the block hash is initially set to blank. It will check it has the leading zeros or not. Well, it doesn't. It will come inside and the nonce value is set to 0. It will try with 0 nonce and it will generate the hash, and it will check if the hash has the 4 leading zeros or not. It doesn't. It will increment the nonce value, generate the new hash. It will keep doing that until the condition is satisfied and the block hash has the 4 leading zeros. And the only thing that we can change to generate a different hash is the nonce value only. In the next line, let's go ahead and add the print statement. With the print statement, we will see that how many hashes are generated before we found the right one. Print mining started self.nonce, and also add and equals to r. We are doing this so that it should not print in every new line. Instead, it should update the print statement. So now we are done with this. Save it. Head back to the core module. Create a new module called blockchain.py. So inside the blockchain.py, before we'll start, we need to import a couple of modules. And before importing them, this is the main file. So we need to define the path. Where should our Python interpreter look for the modules that we want to import? Let's go ahead and import sys and then set the path sys.path.append. Copy the path from here. So all of our modules are inside the Bitcoin directory. Let's go ahead and copy and paste. Change the slashes here. Alright, so now let's go ahead and import the block and the block header module from blockchain.backend.core.block import block header. Alright, also import the hash 256 from the util module. Okay, let's go ahead and create the blockchain class blockchain. Define init method. Inside the init method, create self.chainList. So once blocks are mined, we will add or append it in this chain. Alright, so now we need to create the Genesis block. So Genesis block is the first block in the blockchain. Let's go ahead and create the Genesis block method. Genesis block. Genesis block is the first block, so the block height for this block will be 0. So let's define block height equals to 0 and previous block hash. Genesis block is the first block in the blockchain. Technically, it does not have any previous block hash. So let's add the hash manually. So go ahead and create 0 hash variable, 0 into 64 times. So 64 zeros. Let's assign it to the previous block hash. Okay, so now we need to create the add block function. Let's go ahead and create add block. Add block takes block height and the previous block hash as the input. Block height and block previous block. Okay. So go ahead and import the time module. Import time. Create a timestamp here. Time. Convert it into integer. Go ahead and create transaction. So we will create a dummy transaction for now. But we will create the dynamic transaction, which will change in every block. So let's go ahead and create f string. Code is alert sent. So in order to create the dynamic transaction, we will encode the block height here. So that we have a unique transaction in every block. Bitcoins to Joe. So for Genesis block, the block height is 0. So our transaction will look something like code is alert sent 0 Bitcoins to Joe. Now let's create the Merkle root. Merkle root. The simplified definition of Merkle root is it is the combined hash of all the transactions. Let's go ahead and pass the transaction as an input to our SHA-256 to create the Merkle root. SHA-256 and transaction as an input, encode it before passing it to hash-256. So once we will encode, now whatever output is coming from hash-256, we need to convert it into the hex format. So let's go ahead and do that. All right, so we have the Merkle root. Next is bits. In simple terms, bits is the target. So I'll explain what is bits, but for now, just we are hard coding the bits value in here. For now, just follow along. And now, create the instance of the block header. Block header. So block header class takes the version as an input. So let's go ahead and create the version. So version is the version of your blockchain, which is 1. Pass version as an input. Then previous block hash. Merkle root. Timestamp. And bits. Okay, so we have created the instance for our block header. We have passed the block hash, Merkle root, timestamp, bits. Now we need to mine the block. So in order to mine the block, go ahead and call the mine block function, block header dot mine. And once block is mined successfully, we need to add the block in the chain. So in order to add the block in the chain, let's go ahead and do self.chain.append, create an instance of our block class. Block class takes block height as an input. Then it takes block size, block header, transaction count, and the transaction itself. Head back to the blockchain. The block size, set it to 1 for now. Block header, transaction count, transaction itself. Alright. So basically, we are creating an instance of our block class and then we are appending it in the chain. So now let's go ahead and call this function here in the Genesis block, self.add block, pass block height, and the previous block. So block height for the Genesis block is 0 and the previous block is set to 64 zeros. Alright, let's go ahead and initiate the Genesis block in the init method. Let's go ahead and create the blockchain instance. Blockchain, okay. Okay, let's quickly see if everything is okay. Let's close all other files. So we have created the blockchain class. Inside the blockchain we have created the Genesis block, and then the block height we have set. We have created the add block method. Add block method takes the block height and the previous block as input. Then it creates the timestamp. We are dynamically creating the transactions, and then the Merkle root bits and the block header, and then we are mining the block, and then we are appending that block in a chain once block is successfully mined. Let's go ahead and print the block here in the add method. Self.chain. So once we print the block here, it will show us the object instead of showing us the values in the string format. So let's go ahead and trigger it first, and then we will see how to stringify it. Alright, so we notice that mining was started. It has successfully mined the block. It has appended the block in the chain, and since we have printed the chain here, so as I mentioned earlier, it will show us the block object instead of showing us the data in the string format. So let's go ahead and fix it. So we need to dump the data in the dictionary format here instead of in the object format. So let's go ahead and do dict and do the same for the block class. So if you see it carefully, we did it for both the classes. First, the block header, it's a class instance, so we have converted it into the dictionary, and then we have converted the block class into dictionary. And now let's go ahead and import JSON. So JSON will help us to formulate the data in the correct format, and it will be easy to read. So let's go ahead and do JSON.dumps and self.chain and indent to 4. Now let's go ahead and re-trigger it again. So mining has started. So these are the number of hashes it has generated. So these many hashes it has generated to find the right one, which has the 4 leading zeros. So it constantly changed the nonce value, started from 0, 1, 2, 3, and finally at this value, finally at this nonce value, it found the correct hash. And this is the Genesis block. We have successfully created the Genesis block. We can see the block height is 1, block size is 1, block header has the version like we defined here, the version of our blockchain is 1, and the previous block hash has the 64 zeros as we mentioned here, and then the Merkle root, this is the hash of our transaction, and then the timestamp, the creation time of our blockchain, the bits value we hard coded, nonce value, these many are the hashes it has generated to find the correct hash, and this is the block hash. So this is the hash of our Genesis block. So now this is just the Genesis block we have added in the chain. How to extend the chain so that it will continuously mine the blocks. So let's go ahead and create the new method called main. Create a while loop. Get the last block from the chain. Retrieve the block height. Last block, index 0, since it is returning a list here. So we are looking at the index 0 and get height and add 1 to it. So basically it is getting the height of the previous block. For example, the Genesis block has the height 0. It will get 0 plus 1 and the new height will be 1. And let's retrieve the previous block hash. Previous block hash. Again last block, index 0. And we know the block hash is inside the block header. So let's give it block header and then get the block hash. And now we have the previous block hash. Now we need to call self.add block height and previous block hash. Be carefully, what we are doing here is we are retrieving the last block. From the last block we are getting the last block height, we are adding 1 to it, and then we are also retrieving the last block hash, and then we are passing both of them to the add block method. So add block method will create the timestamp, it will create the transaction by adding the block height to it, it will generate the Merkle root, this value is static here, and then it will create the block header. So block header is taking the previous block hash, which is this one here, and it is combining all these fields together to generate the new block hash for block number 1. And this process continues for all the blocks, and this is how all the blocks are connected with each other. Now let's go ahead and call the main function, blockchain.main, and put the breakpoint here. So first it will try to generate the Genesis block. Alright, it has found the Genesis block. So it has found the Genesis block by generating 14,238 different hashes. Finally it found the hash which has the 4 leading zeros. So now let's go ahead and see that how it is going to generate the block 1. So retrieve the last block. We have retrieved the last block. We have retrieved the last block height, which is 1. We did, last block height was 0. We added 1 to it, and the new block height is 1. And the previous block hash is 000094, which is the hash of our Genesis block. Now we are using that hash as a previous block hash, and we are going to generate a new block hash here. So let's go inside the add block method. Created the timestamp, we have created the transaction. So if you'll see, the transaction has code is alert sent 1 Bitcoin to Joe. This is dynamic because we are coding the block height here. Then it will generate the Merkle root bits, then the block header. We are passing the previous block hash and all those fields together, and in the mine function it will combine all these fields together. Let's go inside the mine function and see what's going on. So it is combining all these fields together, and first it will try with the nonce value of 0, and let's see what hash are we getting. Okay, so with nonce 0 it has generated this hash. So this does not have 4 leading zeros. Now it will again go back and check. It doesn't has the 4 leading zeros, and now the nonce value has been incremented to 1. Now it will try with 1. Let's see the new hash now. And now new hash is 7BF3. Again, it doesn't have the 4 leading zeros. This process continues until it will find the block hash which has the 4 leading zeros. So I'll skip this part for now. So it is generating, it is trying to find the hash. Alright, so the block 1 is mined successfully. So with the hash value, so it took 56,034 attempts to find the correct hash. For some reason, VS Terminal is not showing the output in the correct format. After block number 1, it is directly showing the block number 3. So let's directly match the output in the chain. Open up the chain. Open the block number 3. So block number 3 is referencing to the block hash of block number 2, which is 000088. Let's match it with block number 2. So the hash for the block number 2 is 000088, which matches with the previous hash in the block number 3. And this is how all the blocks are connected with each other. Now if anybody will change anything in block number 2, it will change the block hash. And since block hash is referenced in the block number 3, so all the blocks after block 2 will become invalid. Congratulations! Now you know how blockchain works under the hood. Welcome back. In our last video, we created simplified version of the blockchain. We stored our blockchain in self.chain list, which is a temporary space. We need to find a way to store our blockchain data on a disk. Let's go ahead and do that. For that, we need to create a new directory called database. Head back to the core folder. Create a new directory called database. Inside the database directory, create a new module called database.py. Database.py. Okay, so inside this module, we need to create a new class called blockchain.db. Blockchain.db. Define the init function. Declare the file name in which we want to store our blockchain data. Self.filename. Give the file name as blockchain. We will be using our database module a lot. So let's go ahead and create a separate base class which will control the complete functionality of reading, writing, updating the data. Let's go ahead and do that. Class base DB. Declare the init function. Declare the base path where it should look for our blockchain file. Self.base path. Set it to data. Now create the complete path to read the file. Self.file path. Join it with self.base path and the file name self.filename. So in order to get access to this file name, we need to inherit this base class here. Let's go ahead and do that. Base db. So now this file name will be available here. Also do super init okay. Let's go ahead and create the write function. Write function will take block as an input that we will pass from our blockchain class. And let's go ahead and open the file that we created in the init method. File path, open the file in the append mode. There is a problem with the append mode. If we'll open the file with append mode, it will write the data in the file, but it will not separate the data object. So let me show you what I mean by that. So this is how it will write the data. When we'll append the data in the file, we'll write the block 1, 2, 3, but there won't be any separation. This is okay while we are writing the data, but this will create a problem when we'll try to read the data. JSON.load method will fail when it is not able to find the separation between the JSON objects. So we have to find a workaround to write the data into this file, and so that we'll be able to read the data as well. So to do that, we need to first read the data from this file and then concatenate this block object in that file and then finally write that data. So for that, first we need to create the read function. Let's go ahead and create read function. Inside the read function, first check if file exists or not. Self.file path, import the OS module. If file does not exist, print the message. File self.file path not available. And return false. Okay, in the next step, open a file, self.file path, open it in read mode. As file file.readline. We are doing the file.readline because the entire file is written in one shot. So even if we are doing the read line, it will read the entire file. Let's go ahead and store it in the row variable. Now check if length of the file is greater than 0. Then do json.loads raw and store it in the data variable. Go ahead and import the JSON module. If we do not have any data, so it should return data as blank and finally return the data variable. So let's understand the logic here. So first, when we'll try to create the Genesis block, we will have the zero data in here, and that's the reason we are returning the blank data. But when we have created the blocks, so then it should return us the data, and that data we will use here in the write block. So let's go ahead and use and call the read function here. Data equal to self.read, and if data is returned, to data equals to data plus item. So read function will send us the complete data that we have it on the file, and this line of code will append the new block that will pass from the blockchain class. It will add it in the existing data, and then we will have the final data along with the new block. And if data is empty, so that means it is a Genesis block. Let's go ahead and handle that condition. So for Genesis block, we'll simply return the item in the data variable, and here instead of append, go ahead and do write as file.write json.dumps, and we want to dump the data variable. Okay, so this looks good. So let's quickly go ahead what exactly we did. We created the blockchain DB class, and to handle the read, write, update and the other functionalities, we have created the base class. So this base class will handle all these functions. Then we are inheriting the base class here. We have defined the file name where we want to store our blockchain, and then we have created the read function. Read function will first read the complete data from the disk, and then we are appending the data with the new block in it, and finally we are writing the complete data back in the file. Now let's head back to the blockchain DB and create a new function here. So you remember we need to handle the last block as well, because we need to get the block height and the previous block hash. So let's go ahead and create last block function, self to data self.read. So self.read will again send the complete data here, but we just need the last block. So for that we can do if data to return data -1. So since the data is in the list format, and by doing -1, it will just give us the last block here. And it is the same logic here. From the blockchain class, we will send the data in the list format, and if we have the data, we'll append the data in the existing data, and finally we will write the data here. Head back to blockchain.py. Before we do that, we need to create the data folder inside the Bitcoin. Go ahead and create data directory. So this is where it will store our blockchain. Head back to blockchain class and import our database module here from blockchain.backend.core.database module, import blockchain DB. Cool. So now we need to replace self.change functionality with our disk function. So let's go ahead and remove self.chain, create a new function called write on disk, and this will take block class as an input. Create an instance for blockchain DB. blockchain DB and call the write function. And pass the block that we want to write. Alright, we have to also create another function called fetch the last block. Fetch last block. Create the instance for blockchain DB class. Okay, and call the last block method here and return it. Blockchain DB dot last block. So this will give us the last block. So now we need to change this logic here to write the data on disk instead of self.chain. So let's go ahead and remove this and replace it with self.write on disk. Also change it in list format because we need to send the block input as a list. Alright, so we have changed it. Remove this. Also, you can remove the JSON module from here because we are no longer using here. Also, now we need to get the last block here, right? So do self dot fetch last block, and this will give us the last block, and we don't need to use this anymore. Alright, so let's see what exactly we did. We created two functions, write the data on disk and fetch the last block. It was the same like self.chain. Instead of writing the data in self.chain, we are writing the data on disk. We have created the blockchain DB class here. So inside the blockchain DB, we have created the base DB and the blockchain DB class. And we have created the read function and the write function. So write function is to write the block data into the blockchain file, and read is to read the data from the blockchain file. And finally, we are also returning the last block, and it will just send us the last block that we have written to the chain. So this looks good. Let's verify. We do not have blockchain file yet, so it should automatically create this file once we'll fire the blockchain class. So let's go ahead and do that. Okay, so it is writing the data. It has created the blockchain file here, so that means it has written the blockchain data. Let's wait for a couple of seconds and then we'll see the data in the blockchain file. And this error message is fine because at first we will not have the blockchain file available, and it will fail, and we already took care of that message here. So this is where it is coming from, and we can see it is successfully writing the data to the blockchain file. We have block 0, block 1, 2, 3, 4, 5. Scroll down, and it is continuously writing the data to this file. Just now it has written the block number 38, 39, and perfect. Very well. So we have completed the functionality to write the data on disk. Before moving forward in this course, we need to learn how to create Bitcoin address, and for that we need a elliptic curve library. You can find this library attached in your course material. Go ahead and download it. Once you have downloaded the library, go ahead and copy it inside the code directory. I have copied the library inside the code directory, and we need to also create another directory inside the blockchain directory. That would be client. And inside the client directory, we need to create new module called account. Alright, so now we need to create a class called account. So in this class, we will create our Bitcoin address. So create class account. We really don't have anything to initialize in this class, so we are not going to define the init method. So let's define the function called create keys. So before we start creating our Bitcoin address, we need to learn a little bit about the elliptic curve. So let's understand what is elliptic curve. So the equation for the elliptic curve is y square equals to x cube plus ax plus b. And we are using a very specific equation in elliptic curve, that is SECP 256K1. So the same equation is being used in Ethereum and many other cryptocurrencies. And what is special about this curve is the parameters or the constant values. So in this curve, the value of b is 7 and the value of a is 0. And the final equation will be y square equals to x cube plus 7. We are also going to use few constant values. These values are predefined in elliptic curve and they are constant. They won't change. So the values that we are going to use is gx and gy. So these are the values. So this is nothing but your numeric number, but right now it is in hexadecimal representation. So let me quickly show you the number in numeric form. And to create the Bitcoin address, we need the gx and gy coordinate, and these two coordinates are predefined in SECP 256K1 curve. And the gx and gy coordinate is somewhere on this curve, and since those values are constant and they are predefined, and we are going to use those values now to create our public address. So let's go ahead in our VS Code. And these are the values for the gx coordinate and the gy coordinate. Right now these values are in hexadecimal format, but these are really the numeric numbers. So let me show you quickly the gx coordinate in the numeric form. Type Python, paste your gx coordinate, and you can see the value is in numeric format. Same is for the gy. Copy gy coordinate, and this is the numeric value for the gy coordinate. All right, let me close the terminal and let's start by importing few classes from the elliptic curve library that we just imported. So first we need to import our class called SHA-256 point. So let's go ahead and import it from blockchain dot backend dot core elliptic curve import SHA-256 point. We need to also set the path, so where it should look for these libraries. So go ahead and import sys.path dot append, and you can find the path from your terminal. So for me this is the path. You need to change the slashes to /. Okay, so we have set the path, we have imported the library. Now we need to create the instance of our class. So go ahead and create the instance G SHA-256 point, pass gx and gy to our class, and now we have the instance G for this class. So the elliptic curve equation that we just saw here, that is defined in SHA-256 point. And we need to also import one more library that is called secrets. So let's go ahead and import secrets. So this library is required to create the private key, and we have chosen this library for a very specific reason, because your private key is at the core. We need to create our private key in such a way that it is not easily identifiable or nobody can easily crack it. So that's the reason we are using this cryptographically secure library secrets. And let's go ahead and create our private key. Private key equals to secrets dot random bits, and we are going to give the random bit size as 256 bits because that is the size of our private key, 256 bits. And let's go ahead and print our private key here. Okay, name equals to main. Create the instance of our account class, ACCT equals to account. Nothing to pass here because we do not have any init class, so we are not passing anything here. And go ahead and call the create key function, ACCT dot create keys. Save it and run. Alright, so we have the private key here. Now every time you run the script, it will always give you a unique private key. Alright, so we have a different private key here. Okay, so until this step, we have everything working. So let's clear the terminal and close it. Let's remove the print statement. In our next step, we are going to create our public key from here. So let's go ahead and create the public key. Creating a public key is very simple. So it's a simple multiplication. We are simply multiplying the private key with our G point that we created here, and it will give us the uncompressed public key. And we will also see how to create the compressed public key from that. So let's go ahead and create the uncompressed public key first. Uncompressed public key, private key into G. So this will give us the uncompressed public key. So basically this is returning the x coordinate and y coordinate on the elliptic curve. And now we will extract the x coordinate and y coordinate from the uncompressed public key. So let's go ahead and do that. X point uncompressed public key dot x, copy it, and we will do the same for the y coordinate. Just change the value from x to y, and same for the y point. Okay, so now we have the x point and the y point. Now if you will look at it, we really don't need the x and y point together, because we can easily calculate the x point from y and y point from x, because our equation is y square equals to x cube plus 7. So if we have y, we can easily calculate x from it. So this is how we are going to compress our public key. So we are going to use just one of the point, and we will use the y point in this case. So let's go ahead and see if y point is an odd number or the even number. So this will tell us the y point is the even number. If it is the even number, so we will add a prefix of 02 in front of it. So let's go ahead and define it. Compressed key bytes. So we are going to define that in bytes format. So x02 plus the x point that we created here. So we are going to convert that x point to bytes, because right now it is in numeric form. So let's define x point, and there is a simple function to convert it to bytes. And also we need to define the size of the key. So this is 32 bytes long, so we'll define 32 bytes. And also we need to define if it is a big endian or the little endian. If you don't know what is big endian or little endian, it's a very simple concept. So in big endian we write the number from left to right, and in little endian we write the number from right to left, and that is in bytes representation. So let's go ahead and define big endian here. And if it is not an even number, so we will prefix it with 03. Copy this line and paste it in the else. Change this to 3. In the next step, we are going to run a couple of hash functions to create hash 160. So first we will do the SHA-256 hash, and whatever the output is coming from that output will be passed to RIPEMD 160. That's another hashing algorithm. And then we will have the hash 160, the final hash. Let's go ahead and define that in the util module. So go back to your blockchain backend. Open util. So we need to import a library called import crypto.hash. From crypto.hash import RIPEMD 160. We will define the function hash 160. So this will take the input. Before we do that, we need to import one more library called hashlib. So from hashlib, we are going to import SHA-256. From hashlib, import SHA-256. Return. So first we will do SHA-256 on whatever the input is coming. Then do digest. And whatever the output is coming from that, we will run the RIPEMD on this. So let's go ahead and do RIPEMD 160 dot new. Change this to lowercase s, and whatever the output is coming from this, do the digest for this. And this add back to account, and we need to import hash 160 from the util package. So let's go ahead and do that. From blockchain dot backend dot util import hash 160. So let's put this up. All right. So now that we have hash 160, so let's go ahead and run this function. We will store the output in hash 160 to hash 160 and pass our compressed public key that we just created in this step right here, and this will give us the RIPEMD final hash. So define prefix for mainnet. The Bitcoin mainnet prefix is 1, so we are going to use the same prefix, main prefix. So this is in bytes form. Okay, so we have defined the main prefix. Let's go ahead and add the main prefix to hash 160 that we just created in the step above, and define this as new address main prefix plus hash 160. In the next step, we are going to define the checksum. So checksum is really important while creating the addresses. So it will capture if there is any error in your address while you are transferring money to somebody. So it will capture it. So what it does is, so we are gonna do the hash of this address, and we are going to pick up the first 4 characters from the address and add it in the new address. So let's go ahead and do that. Little documentation about checksum. Checksum equals to, so this is the hash 256, so which means the double hash. So we have already defined the hash 256 here. So we are going to do 2 rounds of hash of this address. So let's define new address, pick up the first 4 characters of the address, whatever the hash is coming from it, assign it to checksum, and the new address is new address plus checksum added to it. All right, so we have added the checksum. In the next step, we are going to define the base 58. Base 58 is nothing, it's just the values or the numbers from 1 to 9 and your A to Z ABCD, and then A to Z your lowercase ABCD. Define count. So in the next step, check for how many zeros are there in our address, and we are just checking the leading zeros in address because we are just concerned about the leading zeros. So let's go ahead and check that. New address, if C equals to 0, then increment the counter that we defined, count variable, else break, because we are just concerned about the leading zeros. In the next step, we are going to convert our address into numeric form. Let's go ahead and do that. Number equals to int from bytes, new address, and it is in big endian, so we need to tell if it is big endian or little endian, and it will convert accordingly in the numeric format. And in the next step, we will do prefix 1 into count. So basically, how many zeros we have found in the address, so we are going to convert that many zeros in the prefix. We are just multiplying that many ones with that number. And let's define result equals to blank. And so in the next step, we need to find a way how to assign the base 58 values to this number. So we need to create a while loop here. Inside the while loop, we are going to use the method div mode and pass number here and divide it by 58. So this will give us 2 values in return. First the number and second the mod value, and your mod value will always be under 58. And in the next step, we are going to do result base 58 alphabet, whatever it is returning here in the mod, so assign it here mod plus result. So let's quickly see what it is doing. So we are dividing it by this number, it will return the mod value, and we know that mod value will always be under 58. So whatever the value is coming here, for example, we got 57 by dividing whatever the number is there. So it will pick up the number from the location 57 and assign it to the result. It will keep doing until we have assigned all the values from our number to the result variable. And I think we are done with this. So in the next step, let's go ahead and assign the prefix that we created in the step above to the result. So the public address is prefix plus result. There is a difference between the public address and the public key. So public address is the final output after doing the base 58 conversion, but your public key is this one, the compressed public key that we created in this step. So there are a couple of steps involved after creating the public key. So we did the hash 160, and then in the next step we have assigned the main prefix, the main net prefix, and we have also created the checksum. And in this step we have assigned the base 58 values to our public key, and now we have the final public address. Let's go ahead and print the private key and the public address that we created. So print private key, and the public address. Let's remove all the spaces from here. Okay, so let's go ahead and quickly check our code if everything is okay. So we have created the class create keys. We have created the private key. We have got our uncompressed public key from here. So we are checking if the y point is odd or even number, and we are assigning the tag accordingly. In the next step, we are doing the hash 160 here. And okay, so change this to lowercase x, and also here change it to lowercase x, and also we missed to get the number because change it to number. Save it, and let's go back to the utility function. And we have the hash 160. It is simply returning the hash, whatever the input we are passing here. And this looks good. Let's go ahead and run it now. And you can see we have the private key, and we need to change the text here to public key. Let's save, delete, and rerun it again. Okay, so for this private key, we got this public key. So this is working as expected. Let's run it one more time. Nice. So for a different private key, we are getting the different public address, and we can see it is starting with 1 because we have defined that this is our mainnet address. In this session, we are going to talk about transactions, and transactions are at the heart of Bitcoin. Transactions are simply value transfer from one entity to another. So let's create our transaction module inside the core directory. Go inside core and create tx.py. Create our class tx. Define init function. It takes version as an input, transaction inputs as an input, and transaction outputs as an input, and log time. Let's assign these values. Self.txins, txins, txouts, txouts, self.log time, okay. So let's understand what does these components mean. Version is simply the version number. For example, you have Windows 8 and Windows 10. Both operating systems has different functionalities. Similarly, in Bitcoins, generally the transaction version is 1, but sometimes it can be version 2. It's just that in version 2 we have slightly different features than version 1. Transaction inputs are what transactions we are using as an input to transfer money to somebody else. So you should have received the money or coins from somebody else before spending them. Transaction outs are to whom you are sending the money. And log time is you are defining the log time on the transaction. For example, if you have defined the log time of 1000 in the log time, so that means that transaction cannot go inside the blockchain until block number 1001 is mined. And let's define the transaction input class here. Class tx in our init function. So transaction input takes previous transaction ID as an input, previous index as an input, script signature. So we need to prove our ownership before spending that transaction. Sequence number. Right now sequence number is disabled in Bitcoin, and by default its value is set to maximum, which is this number. So we are not using this feature, or it is not being used in Bitcoin also. So let's assign these values. Self dot previous transaction. So this is where the transaction ID goes. Self dot previous index. Previous index. Script dot signature. So this is where our signature goes. Self dot sequence equals to sequence. And then we will create our signature to prove the ownership. So let's go ahead and create the script class, and then we'll modify our transaction input class a little bit. So create a class called a module called script dot py. Create class script. Define init function. It takes commands as an input, CMDs. Set it to none if in case nothing is passed to this. So if CMDs is none, we will assign an empty list. Else self.cmds equals to cmds. We'll go through script class in detail, but for now we are just preparing the skeleton for all the classes. Head back to transaction class. From blockchain.backend.code.script import script. Let's modify our transaction input class here. If script signature is none, self.script signature is create an instance of the script class. Else self.script signature equals to script signature. Save it. Let's understand the transaction input components. For example, Bob sent 5 bitcoins to Cody's alert and 5 bitcoins to Joe, and that transaction will have a very unique transaction ID, and this transaction ID will go here. For example, Cody's alert decides to send 2 bitcoins to somebody else, and Since this is the index number that belongs to Cody's alert and this is where we have received the coins, so we will define this index number here. And now let's create next class transaction output class tx out. Define init function. And it takes amount as an input and script public key. Let's assign these values. Self.amount equals to amount. Self.script public key equals to script public key. Amount is self-explanatory, how many coins we are sending, and script public key is to whom we are sending. So this is where we'll define the public key inside the script public key. All right. In this video, we will learn how to create coin-based transaction. Coin-based transaction is a special type of transaction that can only be created by a miner. Miners use this transaction to reward themselves for mining the block successfully. With this transaction, miners bring new bitcoins into existence. So let's create the Coinbase class inside the transaction module. Go inside blockchain, backend, core, and TX. So create a class Coinbase TX. Define init function. This function takes block height as an input. But here block height is coming as a numeric. We need to convert this numeric into byte format, and that too into little endian. Let's understand big endian and little endian encoding. It is just the way of writing the data into computer memory. For example, in big endian, the most significant byte of the data is placed at the lower memory address. For example, this number takes 4 bytes to store in memory, and the most significant byte of this number is stored at the lower memory location. And in little endian, we are doing the exact opposite. The least significant byte is stored at the lower memory address here. And let's encode the logic to convert the numeric number into little endian. So for that we need to head back to the utility module, and let's create a function called int to little endian. Define function int to little endian. So this function takes the number and number of bytes it would require to store that data. Let's add the documentation. Int to little endian takes an integer and returns the little endian byte sequence of length. Okay, do return n dot 2 bytes length. How many bytes are required to store that number, and the notation we are saying it is a little endian. Save it. Go back to the transaction module and do self dot block height in little endian equals to import the function that we just created from blockchain dot backend dot util import int to little endian, do int to little endian, define the block height. But if you will look at the function that we created, we need to also pass the length. So how do we determine that how many bytes are required to convert it into little endian? For that we need to create one more method. Let's create that. Define bytes needed, pass the number as a parameter. If number is equals to 0, return 1 because it would require 1 byte to store. Else we need to import one more library from maths, import log, and what this will do is it will return the bytes that we need to store that number into 256 plus 1. So let me quickly show you how that works. Open the Python interpreter, from math import log, do log, for example the block height is 256, and let's convert it into integer plus 1. So this should give us the result of 1 because the block height is 7 and we know any number below 256 will take 1 byte to store, because 1 byte has 8 bits and 2 is to the power 8, 256. It should give us 1. So now if the number is above 256, it will take 2 bytes. So let's try that. 257, and yes, it is giving us 2. And for example, if number is even greater than that, for example 256 into 256, so this number will take at least 3 bytes to store. So let's try that as well, and give the number as 65536, and yes, it is giving us the 3 bytes. And this is how it will, whenever we pass the number, it will calculate the number of bytes it would require, and accordingly it will convert it into the little endian. So we have defined bytes needed. Go back to the transaction module and import this function as well, bytes needed. And to comma bytes needed and block height. Okay, so now let's define a function called Coinbase transaction self. For any transaction, we know that we would require the previous transaction hash and the index number, but Coinbase transaction doesn't have any previous transaction because technically this is the new transaction that we are creating, so it would not refer to anything, but we still need to create the transaction object. So we will hard code these values here. So every Coinbase transaction will have the previous transaction hash to 0 and the previous index to a specific predefined number. And let's define that. Previous transaction hash equals to 0 underscore hash, and previous index equals to this number. This is a number, but we are writing it in the hexadecimal format. If you notice, it has automatically imported this 0 hash variable from the blockchain module. We don't need this, so let's remove it and define 0 hash manually here. 32 zeros in byte format. Let's create the transaction input object here. So first we need to create empty list txins, And now append the transaction input object to this list. And tx in, it takes previous transaction hash as an input and previous index, and both are already defined here. Now let's create the transaction output as well. So create empty list tx outs. And we know that transaction output takes two variables as an input. First is the amount, and second is the script public key. So let's define the target amount equals to. So one Bitcoin has these many Satoshis, and the Bitcoin mining reward is 50. So let's define it. Reward equals to 50, and multiply the reward with number of Satoshis. Save it. Now to create the script public key, we need to do a couple of things first. First, we need to create the address, minus address that we are using here. So let's go back to the account class that we have created in our previous videos and create the account that we will be using. Copy this private key. Go back to your transaction module. Create variable private key. And store it here. And also copy this address. So this is minus address. Minor address. Save it. All right. Now let's clear this. Okay, so I have saved my private key and the address. For you, the private key and the mining address will be different. So go ahead and save your private key and the address here. In the next step, we are going to decode the address, because we do not directly lock our bitcoins to the address, but we lock it to hash 160. So now we need to create the hash 160 from this address. So let me quickly explain. Go back to your account, and we know that this is what our hash 160 is, and this is what we need to achieve now in order to lock our output to hash 160. So we already have this, so we need to reverse engineer. So what we are going to do is, we know that in hash 160 we added the main prefix, which is 1, and then we added the checksum of 4 characters in our address, and then we did the base 58 encoding in it. And what we need to do is, first we need to reverse the base 58 encoding, and that's exactly what we are going to do. Go back to utility, define a new function called decode base 58. Decode base 58. It takes your address as an input. Number equals to 0. Do for loop C in address, number multiplied by 58, and number, and to base 58. So base 58 alphabet. So we already have that defined in our elliptic curve module, so it has automatically imported from there. And do index C. So what we are doing here is, we are looping through our address, which is this one. So first it will read 1, then L, then Y, and so and so forth until all the characters are read, and then it will check it against the base 58, and whatever value it has read, it will assign that number to the number variable here, and then it will multiply it by 58, and this is how we are going to decode the complete address. Okay, so now let's do combined equals to number to bytes So once we have decoded the address completely, so it will be of total 25 bytes, and byte order is big endian. Byte order equals to big. So if you remember, when we created the address, we defined it as big endian, and now in order to do the reverse engineer, we need to give the same format, big endian, and checksum equals to combined -4. So we know the last four characters in the address is checksum. So we are extracting the checksum from there. And now we will do hash 256 combined the address that we have decoded. Exclude the last four characters because those are checksum, and do the hash 256, and then compare the last four characters. It should be equal to checksum. If it is not, then there is an error. Checksum. So raise value error here. Add address. Checksum. Hash 256 combined -4. So this will show us the result if in case there is any error. And now let's do return combined 1, and remove the last four because the last four characters are checksum, and we also excluded the first one because the first one is the main prefix that we encoded here. We don't need that. We just need the hash 160, and this will give us the hash 160 here. Now go back to transaction. Let's import this decode base 160 and to target underscore h160 decode base 58 and minor address. Now the next step is to create the script public key. For that we need to go back to the script module, and we need to create pay to public key hash script. So go back to script and create a new class method. Class method, define function, pay to public key hash script class. It is a class method, and pass the hash 160 that we just created, and documentation takes a hash 160 and returns the pay to public key hash script public key return script instance of the script class, and define this. Remove these braces, we just need one, And don't worry about these constant values. We are just concerned about the hash 160. As we progress more in our tutorial, you will understand what are these constant values and why we are using it in our script public key hash. But for now, just follow along. We need this. So save it. Go back to your transaction module and define target script equals to script, and use the class method that we just defined, pay to pkh underscore script. Let's see that method name, copy from here, paste it, and pass our target 160. And now tx outs dot append, and we will create the instance of our transaction out object. It takes amount that we have already created, target amount, which is mining reward, and script public key, and for us it will be target script that we just created. Okay, now let's create the transaction object and return it. Return tx, and transaction object, it takes version as an input. Version is 1. Tx input we have prepared, tx ins, tx outs, and log time is 0. So this will return the transaction object. Let's quickly recap what we have done so far. We have created the class Coinbase transaction. We have created the function Coinbase transaction, and we have defined the standard values for the Coinbase transaction, the previous transaction hash, and the previous index. We have created the input. We have created the output. We have decoded the miner address into hash 160. We have also created the pay to public key script, and let's see the script. This should be inside the class, not outside. Let's fix it and save. Go back to your transaction module, and one more thing we need to fix. We have the block height as an input, but we have not used it anywhere, so let's use it. So do tx ins, and 0 means we are reading the first object from the list, and then we are doing script signature cmds dot append, and this is where we are gonna add our block height. And this should be little endian, because when you are creating the objects, so everything should be in the object format. So save it, and now head back to blockchain, and let's import our Coinbase transaction class here from blockchain dot backend dot core dot tx import Coinbase transaction, save. Go to the add block, remove this transaction and replace it with the Coinbase object. So create an instance of our Coinbase transaction class that we just imported. Coinbase instance, Coinbase transaction. It takes block height as an input. So let's assign block height, and then call our Coinbase transaction function that we created. So to Coinbase instance dot Coinbase transaction, and save the transaction object in Coinbase tx. This function is returning the transaction object right here, and that's what we are saving here inside the Coinbase transaction. And Merkle root, set it to blank for now. We will learn in our next videos how to create the Merkle root, but for now set it to blank, and also replace this transaction with Coinbase transaction object that we have created. But there is one more problem. So we are writing the data in JSON format on our disk, but JSON cannot handle the Python objects and anything that is in byte format. So we need to turn our object into dictionary so that we can save it in JSON file. So let's go ahead and do that. Go back to your transaction module and create a new function inside the transaction class. Define to dictionary. Define to dict self, and let's add some documentation. So first convert Coinbase transaction. So Coinbase transaction has the previous hash and block height, but we know our previous hash of the transaction is in byte format that we defined here. So if we are to save it in JSON file, we need to convert it into hexadecimal format so that we can write successfully, because we cannot write byte values. And same goes for the block height. So let's create one more function called is Coinbase. So this will check if the Coinbase it is a Coinbase transaction or normal transaction. So we will be using that a lot, so it's better to create a function. So to is Coinbase self, and how do we recognize if it is a Coinbase transaction? So let's see. Checks. First, check that there is exactly one input, and second, grab the first input and check if the previous transaction hash is 32 zeros in byte format. That will be like this. 232. And third, check that the first input previous index is set to the standard value. And this is how we recognize if any transaction is a Coinbase transaction or not. So save this and let's implement the logic. If length self.tx ins not equals to 1, return false. Next, self.tx ins read the first object of transaction input and assign it to first input. Check if first input dot previous transaction not equals to 32, return false. And next check is if first input dot previous index is not set to standard value, which is this value, then also it is not a Coinbase transaction. So return false. So if all these conditions are false, so that means it is a Coinbase transaction. So then return true. And let's use this function in dictionary to verify if it is a Coinbase transaction or not. So do if self dot is Coinbase. If it is, then do self dot tx ins dot previous tx self dot tx ins. So 0 means we are reading the first object from the list. Previous, and convert it into hexadecimal. Right now it is in byte format. So next is we need to convert our block height into hexadecimal as well, because currently block height is in little endian format, that is a byte format as well. So let's do that. So how to do it? So self.tx ins, again 0th object, script dot signature cmd. This is where we have stored our block height, so convert it to little endian. So we need to create one more function, little endian to int, and let's go ahead and define that function here. So declare it here, define little endian to int. So this will take your input. Let's add the documentation. Takes a byte sequence and returns an integer sequence. So now let's return int from bytes b, and notation is little. So we need to tell it is a little endian and we want to convert it back to integer. So let's go back to transaction and import little endian to int. And do little endian to int and self.tx ins 0 script underscore signature dot cmds and 0th position. So this will convert the block height into integer. And next we have is we need to convert the script signature object into dictionary, because script itself is the object. So let's do that. Self.tx ins 0 dot script underscore signature equals to self.tx ins 0 dot script underscore signature. And there is a simple method to convert it into dictionary. Use this one, dict underscore underscore, and this will convert your object into dictionary. And now in the final step, let's convert the whole transaction input object into dictionary. Tx ins equals to self.tx ins and again underscore underscore dictionary. So we have converted our transaction input into dictionary, and now we need to convert our transaction output into dictionary, the whole object. So let's define that little documentation here about the transaction output. Convert transaction output to dictionary. If they are numbers, we don't need to do anything. If value is in bytes, convert it into hex. Loop through all the transaction output objects and convert them into dictionary. So let's do that. Self.tx outs. Again, we are reading the 0th index because we are reading the first output, and do script underscore public key dot cmds. And we know we have stored the hash 160 at the second position, right? So we need to convert that into hexadecimal. Right now it's in byte format. So let's copy this whole thing and simply do hex at the end. Save it. And do one more thing, self dot tx outs 0 dot script underscore public key, and convert this object. This is a script object and we need to convert that into dictionary, otherwise JSON will give an error. And now finally we need to convert the transaction output object into dictionary, the whole object itself. Tx outs 0 self dot tx outs 0 convert to dictionary, and finally return self dot return the whole object, the transaction object, into dictionary format. So let's quickly recap what we have done. We have created the is Coinbase function here to confirm if it is a Coinbase transaction or not. Let's fix this. And then we did to dictionary. So inside the to dictionary we are calling this function if it is a Coinbase transaction. So for Coinbase transaction we are converting the previous transaction hash into hexadecimal format, and this should be commands, so let's correct it. And here we are converting the script object into dictionary because it is a nested object inside the transaction input right here. So we need to convert all the objects into dictionary because that's the only way to save the data in JSON. And then we are finally converting the whole transaction input object into dictionary. And same goes for output. We are converting the hash 160. Right now it's in byte format. We are converting it into hexadecimal format. And also here we are converting the script object into dictionary. And finally the transaction output object itself into dictionary. And here the whole object, the transaction object, this one, we are converting this into dictionary and then returning. Let's save it and head back to the blockchain class. And now if we will run, so it should work for us. So let's go ahead and clear this file blockchain, save it, and let's set a debug point. Okay, it's already set here, so let's do and debug. So now it should write the data correctly in JSON file because we have converted all the objects and bytes into hexadecimal. So let's see. Okay, so it has mined the block successfully. So go to the next step, and it wrote the first object successfully. Let's check our blockchain file. Go inside blockchain and we can see it has written the first block successfully. The previous block hash is 0. It's good. Merkle root we have intentionally set to blank for now. It's temporary, but we'll add the Merkle root as well. And then let's go and check the transaction. Transaction count is 1, and this is what we have implemented. The version is 1, and transaction input. Okay, so it is pointing to the previous transaction, so which is good. We set to zeros, and the previous index we set to this number. This is good. And we have also set the block height to 0. We converted it into numeric form to save it in JSON format and sequence. And let's check the transaction output, and this is the mining reward. And finally the script public key, we have converted it into hexadecimal format to write it in JSON file, and very well, it worked well for us. So let's write one more block here, and let's check it now, and now it should have the second block as well. And yeah, it wrote the block number 1 as well. So it is working fine. And I think we have done, this is a long video and we have done quite a lot in this video. In our last video, we learned how to create Coinbase transaction. You might have noticed that there is no transaction ID. There should be a unique transaction ID for every transaction. So in this video, we are going to create one. To create transaction ID, we need to convert all the variables in byte format and concatenate them together and then run the hash 256 function on it. So let's do that. So open up your blockchain module, blockchain, backend, core, and transaction. So let's delete this. Okay. So inside the transaction, so we need to convert all these variables and the objects into byte format first, and then we need to create a serialize function for this. So let's define our serialize function for the transaction object or for the transaction class. Define serialize self. So let's understand how this is going to work. So we have version, this is just a variable. So we can easily convert this numeric variable into byte format by doing integer to little endian, and it will be converted into byte. But this is the object itself, the transaction. So we need to create a separate serialize function for our transaction input, and same goes for transaction output. And lock variable is just a variable, and again we can simply convert it into the byte format. So create result variable. So this is where we are going to store everything. So result equals to, so we have self dot version, and we need to convert this into byte format. So let's do int to little endian. So in our previous videos, we have already defined these functions inside the util module, and version by default takes 4 bytes. And next is transaction inputs. So we need to see how many input objects are there in this list, and we can simply do that by using the length function. So do result plus equals to self dot txins and length. So this will give us the number of objects inside txins list. We can have more than one inputs in txins. For example, you want to send 100 bitcoins to George. You need to go through all the transactions that you have received in past from others. For example, we have received 10 bitcoins from Bob, 5 bitcoins from Joe, or 20 bitcoins from Alex, so on and so forth. Since we are sending 100 bitcoins to George, so now we need to combine all those transactions together in order to send 100 bitcoins to George. And now we have multiple inputs, and that's the reason we are checking that how many transaction inputs are there in this list. So the next step is we need to convert this length into byte format. So let's go ahead and do that. Go back to util module, define a new function called encode variant. So we are receiving the number of transactions as an input, and then we are simply returning as a byte. So if the transaction count is less than 253, so we would require 1 byte. If it is more than 254 and between 65,000, then it would require 2 bytes. And we are also adding some kind of prefix so that when we will decode these transactions, so we will know that how many bytes we need to read. And these are hexadecimal values, so we will be working a lot with hexadecimal values in Bitcoin. So let me quickly show you this. Go to Python interpreter, Python, and 65,536. So this is just the hexadecimal encoding of the numeric value. So let's go back to the transaction module and import this function that we just created, encode variant, and convert it into encode variant Okay, so now we have converted the length into byte format. So the next is, since we have multiple objects of transaction inputs, we need to convert each and every object into serialized format. So let's create a for loop for tx in self dot txins and do result plus equals to tx underscore in dot serialize. So now we need to create a serialize function for the transaction input. So let's go to transaction input class and declare a new function called serialize. So to define serialize self, and first we need to convert the transaction hash and then the index. So let's go ahead and do that. So do result equals to self dot previous hash. So by default we know the transaction index is in byte format already, so we don't have to do anything, but we do need to convert the order. So we need to reverse the order. This is how the Bitcoin implementation is, and we are just following the same rules of Bitcoin. So let's go ahead and do that, reverse the order. And next is result plus equals to, so we have the index, and by default index takes 4 bytes, and let's convert it into little endian, into little endian self dot previous index, and it takes 4 bytes. This is a fixed number. And next we have is script signature. So script is the object itself, so that means we would require a separate serialize function for the script class. So let's go ahead and do that. So for now we will simply do self dot script signature. We'll come back to this, and let's convert result plus equals to int to little endian and convert self dot sequence, and self dot sequence as well takes 4 bytes, so we'll define that this is fixed. And finally we will return the result. We'll come back to this. We need to define a separate serialize function for the script object. We'll do that, and let's head back to the transaction object. And now what it will do is it will convert all the transaction inputs, and it will add the concatenated value in the result variable. Let's save it, and let's go ahead and do the same thing for the transaction output as well. So even for transaction outputs, we know that you can transfer money to multiple people in the same transaction. For example, I can send money to Joe, Bob, Christy, Arena in the same transaction if I have enough money, right? So transaction output can have multiple transactions as well. So we need to define the same length function that we defined for the transaction input. So let's go ahead and define that. Result plus equals to, and same function we can use in code variant, and length, since it is a list, so we can do transaction outs, and it will convert the length into byte format. And next we need to convert all those transaction outputs into the serialized format as well. So do tx underscore out in self dot tx outs and result plus equals to tx out dot serialize. So now we need to create a serialize function for transaction output as well. And before we do that, let's take care of the log time equals to int to little endian and self dot log time, and it also takes 4 bytes. So this is fixed. Remove this extra equal to, save it, and finally we will do return the result. Return result. So now let's go to the transaction output and take care of the serialized function. So define serialize, self amount. It's simple. So since this is a numeric, we can do int to little endian like others. And amount is fixed. It takes 8 bytes. So let's do amount and 8 bytes. So it will convert it into byte format. So next is result plus equals to self dot script public key dot serialize. And finally we will do return result. So here as well we have the script object, so we need to define a separate function which is pending in the transaction input as well. So now we will take care of the script serialize function. So let's save it. Let's go to the script module. And in script module, we only have the stack based operations. So that means only push and pop operations are applicable in script. And the functionality of loops is limited in script. And that is because of a few obvious reasons. Because it is possible that if some bad actors push something in script, and because of that, it can go into infinite loop. And this would be an easy way to attack the network. And this attack is called denial of service, or DOS in short. So in script programming, we have two kind of things. So first is the opcodes, and second one is the element. So these numbers, the constant values that we discussed earlier, these are the opcodes. So in script, we have opcodes like hash 256, check signatures, etc. We will see all these opcodes when we will implement the functionality of transaction signatures. And for now, we don't have to deep dive into these opcodes. And let's see and implement the serialized function in script. Okay, so let's go through it and understand what exactly we did. So first import these int to little endian. So to from blockchain dot backend dot util import int to little endian, save it. Okay, now those errors are gone, and we have the encode variant as well. So let's import this one as well, code variant. Let's try to understand the serialized function here, what exactly we are doing. We find the result variable and we have assigned the empty byte here, and then we are looping through the commands, and we know that we have these commands here, and in the script we also assign the commands here. So these are the operations. So this each constant value is assigned to a or tagged to a very specific operation, for example hash 256 or check operations like that. And this is the element, and this is the actual data element, and h160 is the public key where we have locked our bitcoins, and only the rightful owner of the bitcoin can spend or unlock these transactions. So what we are checking here is if command is equal to int, we know that is a opcode, and all opcodes are below 256, and it would require 1 byte to store, and we are converting it into int to little endian. So this is easy one. But if we have something like this, wherein this is the data element, so it will automatically come in the else loop, and then we are checking the length of the command, and if length is below 75, so we are converting that into byte format, And if length is greater than 75 and less than this number, then what we are doing is, so in Bitcoin there are predefined kind of operations already defined. So this signifies that if length is greater than 75, then automatically add the 76 code there, so that when we'll decode the transactions, it will be easy that how many bytes we need to read from the data. And if the length is greater than from this number and less than this, then we are adding a second push data code. So this is a signal that we have 2 bytes to read when we are reading the transaction. So here we are allocating the 2 bytes here. And then finally, we are adding the data element itself in the result. And finally, here we are doing the total length check of the result variable, assigning it to total. And then we are doing the encode variant of total. So it will assign the total bytes of the result that we have plus the result itself. All right. So now we have encoded the script as well. So go back to the transaction, and we have defined this serialization method inside the transaction input class and the transaction output class. So let's check it there right here. Okay, let's fix this. We should have equal to here. So we are doing self.script signature and call serialize here. And we have already called the serialize function here. We have serialized the complete transaction object, and now we can create the hash. And let's go ahead and import the hash 256 from util, hash 256. Go back to the transaction class, create a new function, hash self. So this will return hash 256, the serialized object that we created. So this will return the data in byte format, and we need to reverse the order of the data. This is how it is in the Bitcoin official version, and we are just following the same. So let's reverse the order and also add the documentation here. So binary hash of serialization. And now create one more function, id function. So this function will create the transaction id, self documentation human readable exid return. So this will call the hash function that we created, hash, and it will return the data in binary format or in byte format. We need to convert it into hex. So let's do this. And now we have the id function ready. So we need to modify the Coinbase transaction a little bit. Remove this from here and add one more line, Coinbase tx, and let's call the id function. So do Coinbase tx dot transaction id equals to Coinbase tx and call id. And now we have assigned the new variable transaction id in the Coinbase object. And now let's return this object. Save, go back to blockchain module. Now we can replace this with transaction id. So do Coinbase tx dot txid that we assigned and save it. Clear our blockchain file. And let's call this now. Add the breakpoint. And now we should have the transaction ID created. Awesome, it worked. we have the Merkle root. So that means the transaction ID is being created correctly. There is a small issue with our blockchain. So let me show you the issue. So first let me add the print statement here. Block, add the block height, mined successfully with nonce value of add block header dot nonce. So let me go to the blockchain file. Let me clean up this file. Control A, delete, save the file, and now let's run our blockchain. Okay, so now it looks much better. So we know that which block is being mined and with the nonce value. So let's wait for a couple of seconds. Block 4 is mined. Now block 5 is mined. Let me stop right here. So we noticed the last mined block was the block number 9. So let me select everything, and you can format this in pretty JSON format. And let's look at the last block. So the last mined block was block number 10. Do not save this file when you convert it into pretty JSON format. Otherwise, your JSON dump will fail. So you can use this just to see or view the data, but never save it. So let me close this file now. So let's run it again. You might have noticed that it has started mining the block from block number 0, even though the last mined block was block number 10. So that's an issue. So let's fix it. Let me stop it here. Let's clean our blockchain file. Control A, delete, save. So what we can do to fix the issue? Well, first, in the main function, we can retrieve the last block. Self.fetch. We already have this function to retrieve the last block. So once we have the last block, so we can check if last block is none. So that means there is nothing in the blockchain and it is the first block. So here we can call the genesis block function. So this should fix our issue. We can remove the genesis function from init function, and for now we can add pass here. As we progress in our course, we'll make use of this init function, but for now let's remove it. And I think this should work now. So we have already cleared our blockchain file. So let's test it, run it again. Block 0 is mined, 1, 2, let's wait for a couple of seconds. 3, okay, let me stop it right there. So last mined block is block number 4. So let's convert it into proper JSON format. And last block is block number 8. I think it was very quick, so it has mined the block number 8. So now let's retry it again, run it again. Now it should start from block number 9, not from block number 0. Yeah, it started from block number 9. So this is working fine. And this is how it should work, because we do not want it to start mining from block number 0 every time we stop our blockchain. In our previous session, we defined the function inside the transaction class to sign the input. And now we need to create the functionality where a user can send the bitcoins to somebody else. But before that, we need to take care of one thing. I have noticed that inside the account module, there is a minor typo mistake here. So let's fix that. It's public address. Change it to address and also fix this. and inside the data as well, since we have already added a couple of accounts. So go ahead and search for this keyword. You can do Control C and Control F. Type the copied keyword. Click on this drop down. Change it to address like this and click this button. So it will change everything, public address everywhere. So save this file, close it, and now let's go ahead and define our new module, which would be send BTC. Send BTC.py. Create a class send BTC. Define the init function. This function takes arguments from account. So this means the account of the person who is transferring the Bitcoin, to account to whom you are transferring the Bitcoins, and amount, how many Bitcoins you are transferring, and UTXOs. UTXOs are unspent transactions. Miners keep track of all the unspent transactions. So when you request that you want to transfer money from your account to someone else, this is the place where miner will go and check if you have enough coins to transfer to someone else. So let's go ahead and define rest of the fields. And define one variable here, self.coin, and define the value of 100 million. This value is in Satoshis. So we need to convert all the Bitcoins into Satoshi. And then do self dot from public address. From public address equals to from account. Self dot to account equals to account. Self dot amount equals to amount. It's amount, not amounts. So let's correct this into coins. So we are converting it into Satoshi. And last is self dot UTXOs equals to UTXOs. Save it. Now we need to define the function to create our transaction and sign the transaction. So let's go ahead and define the skeleton of our function. So define a function prepare transaction. So inside this function, we need to define a couple of other functions. So first one would be prepare transaction input, self dot prepare tx in, and the next one is self dot prepare tx out. We know these are the two main parts of the transaction input and transaction output. Let's save it and let's go ahead and define these functions. First, let's declare the function for transaction input. Self. Let's remove this part and add pass. Do the same thing for the transaction output. Prepare tx out. Self. And add pass here as well. So first, let's start with the transaction input. So for transaction input, first we need to define the list, empty list, tx_ins, and then self dot total equals to 0. So how do we prepare the transaction input? In order to prepare the transaction input, we should already have some coins with us. That means we should have received the coins from somebody else in past, or in our case, since we are the miner, so we have the coins from our Coinbase transaction. So let's go ahead and understand that. Go inside the blockchain file, select all, convert it into JSON format. For example, this is the transaction we want to use, where we want to transfer, let's say, 10 Bitcoin to somebody else, and these 50 Bitcoins are locked to our public key hash. And one important point to note is the end user would not know what is their public key hash, so they will give their public address, which is this one. So once they will give their public address, at the backend, convert this public key address into public key hash, and then we need to find that what all coins are locked to you or the end user. So let's go ahead and define the functionality for that. So go inside sendBTC, close this file. So just now we saw our Bitcoins are not locked to our public address, but to the public key hash. So now we need to find a way to decode or convert our public key address into public key hash so that we can find out all the coins that are locked to our public key hash. So we already have the function defined for that. If you remember, decode 58 will do exactly same. So let's go ahead and import that function from blockchain.backend .util import decode base 58. Now let's go ahead and define the function to convert it. Define script public key. This will take the public address as the input. Public address, and then to decode base 58 and pass your public address, and it will give you your public key hash. That would be H160. Save it. And we need one more thing. Let's go ahead and import the script module from blockchain.backend.core.script. Import script class. So what we will do is we will create the script public key because we will be using that in future when we are signing the transaction. So let's go ahead and prepare that as well. Public key equals to script and call key to public key hash, not inside but here, p to pkh script, and pass H168 and save it, and then return script public key. Now go inside the transaction input and add little documentation here. Convert public address into public hash to find TX outs that are locked to this hash. Save and do self.script public key. Pass your address from, and then add this to another variable, self.from address script public key. And one last thing, self.from pub key hash equals to self.from address.cmds. Since we have prepared pay to public key hash, we know the H160 is stored at the second location, and we will use that to find the outputs that are locked to our public key hash. In the next step, we are going to define the functionality to find all the outputs that we are going to use as an input here. So go ahead and define new UTXOs empty dictionary and do try and do while length new UTXOs less than 1. I'll explain in a bit that what exactly we are doing here. New UTXOs equals to dict self dot UTXOs and then do time dot sleep 2 seconds accept exception as E and print the message error in converting the managed dictionary to normal dictionary. Let's fix all these errors here. First, let's import time. And this part as well. This should go underneath try. Save. So this UTXO is your managed dictionary, which means we have created or we will create a dictionary that is shared between processes. And here we are converting that dictionary into a normal dictionary because it has all the unspent transactions. And this is where we will check that which transaction belongs to which public key hash. So let's save it. And in the next step, go ahead and define the logic for TX byte in new UTXOs. Since it is in byte form, so that's the reason I'm using TX byte. If self dot total is less than self dot amount, then do TX object equals to, so we are reading it from dictionary, TX byte. And now we will run the for loop for index TX out in enumerate TX object dot TX underscore outs. If TX out dot script underscore public key dot cmds to equals to self dot from public key hash, the one that we have created in this step here. So we are checking it against the outputs that are locked to this public key hash. Then do self dot the total number of coins that we have in that transaction, TX out dot amount, and previous transaction hash, so which is TX object dot, we will do ID, so it will create your transaction ID, and that we need to convert it into bytes. So do bytes from X and pass this as a argument. Save. And in the final step, we will create the transaction input object and we will add it in the list that we created here. txins dot append txin So we have the previous transaction hash that we are going to use as a transaction input, previous tx hash, and the index. Let's import transaction from blockchain dot backend dot core dot tx, import transaction class, transaction in, tx out, and transaction class itself. All right. And what exactly we are doing here, for example, if you want to send 100 bitcoins, we have already seen that example. We want to send 100 bitcoins to somebody, but we do not have enough money in the one transaction. So we will combine multiple transactions. And this is exactly what we are doing here. If we want to send 100 bitcoins to somebody, and if that money is not enough, so we need to combine multiple outputs here. And that's exactly we are doing here. And when it has reached the 100 bitcoins, then we don't have to read further transactions, so we can simply break out of the loop. So add else and break. Also check if self dot total is less than self dot amount. So that means we do not have enough coins to send. So add the message is balance enough, and add false here because we do not have enough balance to send. And finally, if there is no error, then simply return txins, which is our transaction input object. Yeah, this should be commands. So there is a typo right here. Change it to commands, and also the for loop should go inside the if statement. And now this is perfect. We have if, and if we have the total amount greater than the amount we are looking for, then it should break out of the loop. Perfect, save it. So in the next step, we are going to code our transaction output logic. So let's go ahead and define that. Define tx outs list, which is empty. Then self dot script to public key, self dot to account. So convert this account address into public key hash to script pub key. This is a script public key. So we are locking the coins to the specific person to whom we are sending. In fact, to his public key hash. And then tx outs dot append tx out object, which takes self dot amount comma to self script public key. So we are locking the coins here, and this is in caps. Save. Now let's calculate the fee. Calculate fee. So we need to pay to the miner to include our transaction in a block. So do self dot fee equals to self dot coin. So basically we are saying that we are paying 1 Bitcoin to add our transaction in a block. So 1 Bitcoin as a fee. Then do self dot change amount equals to the total coins that we have here. So for example, we are trying to send 900 bitcoins to somebody else, and by combining all the transactions we have total 1000 bitcoins. So which means we are just sending 900 to someone else, so rest of the 100 coins we need to send it back to ourselves as a change. So let's calculate it. Self dot total coins we have minus self dot amount that we are sending minus self dot fee, which is 1 bitcoin we are paying here. So rest of the coins should go back to us. Let's try to understand this with one more example. For example, you went to Starbucks, you purchased a hot chocolate which is of $5, and you paid $10 to the shopkeeper. He gave or returned $5 back to you, and that is your change. And this is nothing different from that. You have total 1000 bitcoins, you are sending 900 to someone else, and this fee can be considered as a service tax or the fee that we are paying to the miner, and the rest of the change will go back to yourself. I hope it is clear now. So let's create one more transaction output. Tx outs dot append tx out and define self dot change amount self dot from address script public key. So we are locking these coins back to ourselves. So if you look at this, we have two transaction output. The first one, the person whom we are sending, and the second transaction output is back to ourselves as a change amount. And finally return tx outs object. So now we have our transaction input and transaction output method ready. So let's go ahead and prepare the transaction object itself. So let's add this to self dot tx ins and this one to self dot tx outs. Save and prepare the transaction object. Self dot tx object, which will take your version as an input, which is 1. Then self dot transaction inputs object that we just created, self dot tx outs, and the log time. Save. And finally we need to create a new function to sign our transaction. For now we have just created the transaction, now we need to sign the transaction. So let's define the new function. Define sign transaction self. So for that, what we need a private key, right? So let's go ahead and define a new function called get private key. So define it here. Get private key self, and first we need to import the account DB. So let's go ahead and import that from blockchain dot backend dot core dot database import account DB. Save it, come back to our method get private key, create all accounts variable and do account DB and read. So this will return us all the accounts that we have. Change this to this and save it. So the next step is read all the accounts and run a for loop. So do for account in all accounts if account public address is equals to self dot from public address, then return our private key. Private key. Let's quickly verify it. So inside the account file, we have the public address. This is the one that user will pass, and by using this address, it will return the corresponding private key, which is this one, private key, and the public address. So variable names are matching public address and the private key. All right, so we have the private key now. So save this. So let's go back to our sign input function. So now call this and define a variable secret, since it is our private key. Self dot get private key, and we need to import one more class, which is private key, and that will be from the elliptic curve library, from blockchain dot backend dot core dot elliptic curve import private key. Okay, go back to the sign transaction and do brief and the instance of our private key secret equals to the private key that we got from here. And finally, we will do from index input in enumerate and self dot tx ins. So if we have multiple inputs, so we need to sign each and every input, and that's what we are going to do here. Tx object dot sign input index your private key self dot from address script public key. So if we have multiple inputs, so first it will sign the first input, then second and third. So each input should have the script signature, and finally return true. Save it, call this function here, self dot sign transaction So our complete logic is dependent on the transaction input. And if you remember, we are returning this if we have the enough balance or not, just in case if somebody tries to send more coins than they own. So we should not run into issue. So we need to handle that situation. Also add self dot is balance enough equals to true by default. And if in case balance is not enough, it will set the flag to false. Save it. So let's go ahead and check if self dot is balance enough. If user has the enough balance, then only we should run all these steps. Otherwise, it should fail. So return true here. And if we do not have the enough balance, then it should return false. So we don't need to run the rest of the steps. And this return statement we will use when we'll create the front end. So it will be helpful to display the error message just in case user is trying to send more coins than he owns. So we will display the message he does not have the enough balance or some kind of error message. And I think we have done pretty much everything to sign and create our transaction. So let's quickly recap it. So we have created this class. So user will pass the from account to account, amount, and the UTXO. So this is where all the unspent transactions will be. And then finally, we will prepare a transaction input and transaction output. And once we have the transaction input and transaction output, we will sign the transaction. And that's pretty much we are doing in this class. Next topic is how to create and sign transactions. But before we jump to that topic, we need to take care of one thing first. So if you remember, we have created the account class. So let's see that inside client and account. So if you remember, we are not writing the public and private key anywhere. So since we are going to sign the transaction, so instead of keeping track of our private and public key manually, so it's better to write it in a file. So let's go ahead and do that. So go to your database class, core database, database.py. All we need to do is create an account db class here. So we can just copy and paste this exact setup. Replace blockchain db with account db. Since base class has all the methods to write, read, and delete the data, so we will use that. And all we need to do is just replace this file name with account, so that when we write the data, it should write the data in the account file. It will create a new file if it is not there. And that's all. Now we can go back to our account.py, import the class that we just created, blockchain.backend.core.database import account db. And now here all we need to do is just write the data. So do account db dot write. And one more thing, so we are using the local variables right now, for example, for the private key and the public key. So let's replace those local variables with the object. So change private key to self.private key. And do the same thing here where we are printing it. And also change the public address to self.public. Okay, let's quickly see. We have changed it everywhere. All right, so now we can simply write this into our account file. ACCT, which is our object, dot dictionary. And this should write the data into our account file. Okay, let's go ahead and test it. Right now, I do not have any account file here. So once I'll run it, so it should create a new file and dump the private and public key that we are going to create now. So let's run it. Okay, so it has created the private key and the public key. And it has also created the account file here. So now it should have the same private and public key in this file. And I can see the public key is there, starting with 152 and the public address 1IC2. Let's run it one more time and it should keep writing the data. Okay, so the new public address is this and the private key is this. Let's check it out. And we have the new public address and the the private key. All right, so we are done with this part. Let's jump into how to create and sign transactions. Signing a transaction is one of the most important feature in the Bitcoin blockchain. By adding your digital signature in the transaction, you are telling the miner that you own these coins and you are eligible to spend them. Miner will independently verify your digital signature, and if it is valid, your transaction will go through. Otherwise, it will get rejected. So how do we create a digital signature? Go back to your transaction module, go to blockchain directory, backend, core, and transaction, and create a new function called sign input. So this function takes 3 arguments: input index, private key, and script public key. So first step in signing a transaction is we need to calculate the signature hash. So how do we do that? For now, just pass it here and create a new function called signature hash, sig hash. And this function takes 2 arguments as an input, your input index and script public key. Add a pass here as well. So let's call this function here z, which is your signature hash, self dot signature hash, pass input index and script public key. Script public key. Let's go back to signature hash. So how do we create a signature hash? Creating a signature hash is not that difficult. In fact, we have already seen that when we created the transaction ID. So basically, what do we need to do to create a signature hash is we need to convert all the fields in byte form first. And let's look at the transaction object. So this is the object that we have. First, we need to convert the version number and then the transaction input object and then the transaction output object and the log time itself. And since these are object itself, so whatever variables are inside these objects, we need to convert them into byte form as well. We have already seen that in transaction ID, but just a recap. So let's do that. Go back to sig hash function and start converting it. Declare a variable string as here and int to little endian. First convert the version number, self dot version, and it takes 4 bytes. And the next is plus equals to encode. The next object is transaction input. So we need to encode the length first, that how many transaction inputs are there. So let's do that. Length self dot tx ins. And now we are going to convert all the transaction input objects. So declare a for loop here, I for index, tx underscore in for transaction input object, and enumerate to self dot tx ins. Now if I equals to the index that we have passed, go inside the loop and do string plus equals to, create a transaction input object and pass tx underscore in. It takes previous transaction hash as an input, tx, and then previous index, tx in dot index. And next is script signature, so which would be script public key in this case. And we don't need to pass the sequence because it's already there in the object. So let me show you here. Yeah, sequence is already defined here, so we don't need to pass it. So until here, we have just created the transaction input object. Next is call the serialize function to convert it into byte format. So this function is already defined here. It will convert everything into byte format and return the result. And that result will go in the string variable that we have defined here. Now copy this and define the else part. In the else part, there won't be script public key. So let's remove that and let me explain why is that. Open up your blockchain file, select everything and convert it into JSON format. For example, this transaction belongs to us it is locked to our public key, and this transaction also, it is locked to our public key. And we want to transfer 900 bitcoins to somebody. Okay, so we know that one transaction is not enough because this transaction has only 500 bitcoins. So in order to transfer 900 bitcoins, we need to combine at least two transactions. So 500 in this transaction and 500 in this transaction. So we will combine those two transactions and then we will sign them. And that's exactly we are doing here. And also each transaction has the script public key, right? And that script public key goes here, right here. So this is where this public script public key is coming from. So now we have selected two inputs, right? So we can sign each input one by one. So first it will sign the first input with its script public key, then serialize it, and the second transaction will go into its else part because we can sign only one at a time. And then again, we will call the sig hash function with the second transaction's input index. When the index matches here, it will sign the second transaction with its public key, script public key, serialize it, and then the first transaction will go here, right? And it will serialize it. And that's how it works. I hope it is clear. In the next step, we are going to encode the length for our output. So let's go ahead and copy this part and do tx outs, and also run the for loop here to convert the transaction output object. So for tx out in self.tx outs, and do string plus equals to tx out dot serialize. And this will convert the object into byte notation and concatenate everything. And the final step is, let's convert the lock time as well into little endian self.lock time. And we know lock time takes 4 bytes to store. And the only difference between when we created the transaction ID and the signature hash is we are adding one more thing here, that is hash type. So let's define that variable first. Define hash type here, which is 1 numeric format, and convert this hash type into little endian. So let's go ahead and do that. S plus equals to int to little endian sig hash all. It takes 4 bytes. Sig hash all is the hash type. This is to specify what the signature is authorizing. The signature can authorize this input to go with all other inputs and outputs. However, there are other hash types out there. Since we are doing the Bitcoin implementation, this is the most widely used. That's the reason we are using this one. In the next step, we are going to convert this into double hash. So let's go ahead and do that. Hash 256 and hash 256 and the string that we have created. In the final step, we will return the signature hash to int from bytes, and the h256 that we have just created, convert it into big endian, and this will give us the result. So this is the signature hash. Creating signature hash for Z was the most complicated part in the transaction input signing process. So now in the next step, we are going to create the signature itself. So let's go ahead and do that. Define DER and then private key. So this private key is actually the object, and it is coming from the elliptic curve library. And do sign. This is another function to sign the transaction. So let's go ahead and do sign. And Z is that we just calculated in our previous step, and DER. And now we have the signature. There is one more step to that. So let's do sig equals to DER plus sig hash all, convert it into bytes in big endian. and this is our signature. And we need one more thing, so that is our public key. And when we have the private key, we can easily create our public key from that. This is no different than what we have done when we created the account, but we have this function defined inside the elliptic curve as well, so we'll make use of that. So let's do SEC. That means it is a compressed public key. So to private key dot point dot SEC, and now we have the compressed public key. So in the next step, we are simply gonna assign the signature that we just created to our inputs script signature. So let's go ahead and define this self dot txins, and the index for which transaction index we are adding the signature, define that index, and script signature script underscore sig equals to create a script object here, script, and then pass sig, which is our signature, and the public key. And that's it. We have successfully signed our transaction. Okay, so we have designed the backend class to handle the logic when user will send the coins to someone. Now we need to design the front end. So we will be using Flask for the front end. So let's go ahead and create a new directory inside the front end. So create templates. So this is where we'll keep our templates. So this is where we'll keep our HTML files. So create a file called wallet.html. So for front end, this is the logic we have. It's a very simple logic. So what exactly this is the standard HTML tags. So we have attached the style sheet here that we will develop, and then this is the important one. So we have created the division element, and we have created the wallet container to style our division element, and also we have defined the hashtag send bitcoins, and this is the form where a user will enter the input. And also we have defined the message if in case we need to display any error message or any information message, so we'll use this message tag here. And otherwise it's a very simple. So from address, this is a label, and this is the input tag where user will enter the text, which means the from address. And then we have the to address. This is where user will give the to address, then the amount, which is in numeric form, and this is a submit button. And that's pretty much we have it in the HTML form. So let's go ahead and define the static file here, static directory, and inside the static directory we will create style.css. Okay, and one more thing we are going to do is now we will create the logic to display the form. So let's go ahead and create one more module, run.py. So this is where we will define our Flask logic. So go ahead and import from Flask, import Flask and render template and request. You should already have Flask installed, because when we install the requirement.txt, it had all the modules. Just in case you don't have it, just do pip install Flask and you will have the Flask installed on your system. And the next we will import from blockchain.client blockchain.client send btc, import send btc, save, and create an instance for the Flask. This is a standard. We'll create app and then define a function wallet. This function we will use to display the HTML form that we just created, wallet.html. And to display, we need to also define the route. So let's go ahead and define app.route. So by default, it should display the wallet form, and methods will be using get and put, because we will be sending and receiving the data. So we'll use both get and post, not put. Methods equals to. Okay, so now next is check if request dot method equals to post. That means user has entered some data and hit on the submit button, so we will receive something, and now we are going to receive the data from the form that user has entered. And let's go ahead and define from address. So first receive the from address that user has entered. Request dot form dot get from address, and this from address variable is already defined inside the HTML form, if you'll see it here. So this is from where we are reading these variables, from address, and same will apply for to address and amount. Let's copy this 1 and 2, replace it with the to address, and same goes here, to address, and third is amount, and do amount, and we have defined the amount as integer, so let's define type equals to int. By default it's string. And now let's go ahead and create the instance for our sendBTC class that we have imported. So do sendBTC, and we know that sendBTC takes from address, to address, amount. It also takes UTXO. We'll get there, but for now just create the instance here. Send coin. So this is the instance we have created, and so next we will call the prepare transaction function that is defined right here, prepare transaction, and if it is a success it will return true, otherwise false. So let's go ahead and call this function here, send coin dot prepare transaction, and define the if condition, since we are returning true and false flag. If not, so that means there is an error, so we will define the message equals to insufficient balance. So if you remember, we have also defined the message tag here, so by default message will be blank. If there is an error, so it will display this message, and finally we will render the template. So let's do return render template and pass wallet.html that we created, and also pass message equals to message. So this message is replacing the message here that we have defined here. So basically it is replacing or updating all the fields that are defined in this HTML form, and we are updating it via Flask from here by using render template. Let's save it, and the next step is main, and this is where we will receive the UTXOs. Define it as a global variable UTXOs, and then do UTXOs equals to the one that we have received in the function as a parameter. And finally app.run. Save it, and that's it. Let's quickly check if we have done everything. So we have created the Flask app instance, we have defined the wallet, and we have also defined the route. So when we will hit the URL, by default it will open the wallet page, and it will render this page HTML wallet.html. And now we need to take care of one more thing. So go to blockchain, and inside blockchain import from multiprocessing, import process and manager. And now we need to understand why are we doing that. Because our front end will be running in a separate process, and the back end, which is blockchain, it will be running in a separate process. We can run it in the same process, but then it will slow down our mining, and we don't want to do that. So most of the laptops has, I think, 5 to 7 cores of the processor. So it's better to run the processes on separate processor so that it will be fast. And the only caveat with that is it's very difficult to share the data between processes. If you are running everything in a single process, you don't have to worry about the data sharing. Data sharing is very easy. But in multiprocessing, we have to take care of data sharing manually. We have to find a way so that we can share the data between processes. So since front end is a different process, blockchain is a different process, our UTXOs are created in the backend process, which is blockchain. And we need to share it with the front end as well, because once we'll receive the request from the user, we have to check that if user has enough balance or not. And the only way to check that balance is if we'll share the data between processes. So let's go ahead and define that. So we need to create a shared dictionary. So, and in that dictionary, we will save our UTXOs. So right here, create with manager as manager, create UTXOs. So this is the dictionary we are gonna create with manager, special type of function. So this will create a shared dictionary, and we will be able to use this dictionary between the processes. And let's move them inside this. Also, let's import the main function from the run module from blockchain dot frontend dot run import main. So let's go ahead and trigger this process. So the way to run this main function in a separate process is like this: process target equals to main, and make sure you are not giving the main function like this, otherwise it will execute it. We need to give main function just the definition of the function. And arguments, yes, we are passing the arguments as a UTXO. So UTXO is the only argument we are passing, and then we need to start the process. So let's assign it to a variable web app, and then let's start the process. Web app dot start. So this will start the process, and now we will be able to share the data. Whatever data we'll update in the blockchain module, it will be shared in the front end as well, which is in our run module. So now let's go ahead and allocate or assign the transactions to UTXO. So let's pass UTXO here as well. UTXOs, and go in our init method, and let's pass UTXOs and do replace pass self dot UTXOs equals to UTXOs. Save it. So let's define one more function. Define store UTXOs in cache. So this is a cache memory where we are storing the UTXOs self and then transaction, and do self dot UTXOs transaction dot txid. Since it is a dictionary, so transaction ID would be our key, and then transaction itself will be stored in UTXO. And let's define the documentation. Keep track of all the unspent transactions in cache memory for fast retrieval. So we are doing this for very reason, so that we can quickly retrieve the data from the cache memory. And even in actual Bitcoin blockchain, the unspent transactions are stored in your cache memory. So let's go ahead and call this function inside the add block right here, to self dot store UTXO in cache. Right now we just have the Coinbase transaction, so let's pass this here and save it. Okay, so we are done with everything, and let's quickly verify. So we have defined the shared dictionary. Now we will be able to share the data between processes. And inside the static, we need to create one more directory inside static. It should be CSS, and then we should move the style.css inside CSS. Save it, and now let's run this process, and hopefully we will have the front end up and running now. Yeah, one more thing we need to take care is inside the run module we passed the UTXO, so that we are receiving it here. So let's pass this UTXO here as well inside the send, and I think that should do. So let's run it. Okay, so we have the front end started. So let's open up our browser. Cool. So we have the form rendered successfully. This is what we defined inside our HTML, but right now this is just a plain form, so we need to style it. So let's go inside the style.css and copy and paste the CSS you have attached in your course, and then it will look good. So copy and paste it here, save, and let's refresh the form and let's see if we have the changes. Cool. So we have the form rendered and it looks beautiful right now. So we have the from address, to address, and the amount. Okay, so our front end is up and running, but we won't be able to transfer coins from here right now. If you remember, inside the transaction module, we are using private and the miners public address, but this address is not saved inside our account file. And if you remember, our send BTC method is checking for a private key inside the account file right here. So since those keys are not there, so it will fail. So we need to save these keys inside the account file. So let me copy them. Copy the private key. Go inside the account file. I'll replace this private key with the one that we need, since we are not using this account, so it's okay. And also the public address. Copy this, go inside account file again and replace your address as well. You can either add or replace, so I just replaced it. So now we can try sending some coins from here. So this is the address. I'm sending 5 bitcoins to this address, and hopefully it will not throw any error. Yeah, so we do not have any error. That means it worked perfectly fine. So in the next session, we will see how to include those transactions inside the block and how to verify them. In our last video, we saw how to create a transaction and sign it. In this video, we will learn how to verify the transaction. So the first thing that we need to verify the transaction is calculate Z, which is your signature hash. And we have already seen that when we sign the transaction. So let's go ahead and create a new function called verify transaction. Verify input. And this function takes 2 arguments. First is your index of the transaction that you are verifying. Index. And the second one is script public key, to which public key the bitcoins are locked. Public key. So let's go ahead and extract the object that we are verifying, the transaction input, based on the index that have been passed. Input index. So here we are extracting the input transaction input object that we are verifying. So there can be multiple transaction inputs, so we need to specify which transaction input we are verifying first. There could be multiple, so let's go ahead and extract that. So once we have the transaction input, we need Z, and we already have all the functions in place to calculate Z. So let's do self.signature hash, and it takes the input index and script public key. Until this step, we know that the user has already signed the transaction, so that means the signatures are already there in the transaction input. So in the next step, what we need to do is we need to combine the signatures with the script public key where your bitcoins are locked. So let's go ahead and do combined transaction input dot script dot sig is where we have the signatures plus script public key. So you might be wondering, how can we add 2 objects here? Well, we cannot, but we have an alternative approach to handle this. So what we can do is, we know that this is a script object, so we can override the add function here. So let's go ahead and override the add function with our custom functionality. So what we are going to do here is define add self and other, and do return script and do self.cmds. So ultimately we are adding commands, not the objects, and other.cmds. And CMDs are your list, and we can simply add by using the addition operation. And that's exactly what we are doing here. So we have added this. So by doing this here, let's go back to our transaction object. Now your normal addition operator is overridden by this function that we have implemented, and it will add your commands. Okay, let's go back. And the next step is we need to evaluate the signature, right? So let's do return combined, the combined script we have, and do evaluate, and z is the main part to verify your signature, so we need this. And now we need to create a new function called evaluate inside the script, right? Before coding the evaluate function, let's understand how Bitcoin network verifies your transaction. Bitcoin use something called stack-based programming. A stack is a very simple data structure which can be visualized as a stack of cards. A stack allows two operations, push and pop. Push adds an item on the top of the stack, pop removes the top item from the stack. So we just noticed that we have combined our script signature with our script public key. So the first item it will push on the stack is your signature, and second it will push the public key, and then we have the operation which will duplicate your public key, and next it will run the hash 160 on your public key, and then we'll have the hash 160. So after we have the hash 160, so it will run the equal operations, so to compare the first two items on the stack or the top two items on the stack. And if the hash is equal, so then we'll have only two items left on the stack, the signature and the public key, and then it will run the check signature function on top of these two items, and if signature is valid, the final output on the stack will be true, and that's how it will verify the signature. Now let's go ahead and encode all the functions that we need to verify the signature. Let's define the evaluate function inside the script module. So do define evaluate. It takes z as an input, and for now let's pass this. Before creating the evaluate function, we need to understand a little bit about the script public key. And we have seen that we are locking the bitcoins in this script public key, where this is our data element which represents your public key hash, and these numbers which are in hexadecimal format, these are tied to each operation code or the function. For example, the first one, this one is number 118, this is 169, this is 136, and this is 172. Each one of these tags are tied to the operation code. So let's go ahead and define the operation code first. So inside the elliptic curve, let's go ahead and define one more module, op.py, which is your operation codes. So let's define op underscore code underscore functions equals to 169. First we have 118. So 118 is to duplicate whatever you have it on the stack. Second one is 169, which is op underscore hash 160. So this will calculate the hash 160. And then we have 172, which is tied to this function op underscore check signature. And there is one more, 136. So let's add it in the sequence here. 136 op underscore equal verify. Let's put this down and add them in proper alignment. Save it. So now we are going to define the function definitions. First, let's define op underscore duplicate function. So do define op underscore dup. It takes stack as an input. We'll go through what is stack, but for now just implement this function first. and check the length of the stack. If it is less than 1, then return false, because there is nothing on the stack to duplicate it, so return false. And next is, how can we duplicate the element? Well, it's easy. So we can simply do stack dot append whatever is the last element on the stack, add it back, which would be easy by using this list function, and save it. That's about our op_duplicate function. So it will duplicate the last element on your stack. And the next one is hash 160. So let's define hash 160. Define op_hash 160 stack, and check if length of the stack is less than 1. So that means there is nothing there on the stack, so we cannot calculate anything, and return false. If there is an element, so then pop the last element from the stack. So do element stack dot pop, and then we can run the hash 160 function. We already have our hash 160 function. We just need to import it here from our util module. So let's go ahead and do that. From blockchain dot backend dot util import hash 160. Save it. And now let's use that function to calculate the hash 160, which is h160 equals to hash 160 and element that we just picked up from the stack. Then append it back on the stack for further calculation. Append h160 and return true. The next function that we are going to implement is equal verify. So let's see that. Define equal verify. Again, it takes stack as an input, and do pass here. We need to implement 2 more functions before we can make use of this function. So let's define op_equal, and again stack is common in all these functions. Let's add a space here and do if length of the stack is less than 2. Since we are performing the equal operation, so we are expecting at least 2 elements on the stack. If we don't have 2 elements, so that means we cannot perform this function, and return false. And then extract those 2 elements from the stack and use element 1 equals to stack dot pop. So it will pop the last element from the stack. Copy this, enter, and replace this with element 2, and this will extract the second last element from the stack, and then we can just perform the comparison between those 2 elements. If both are equal, then append 1 on the stack, otherwise 0. So do if element 1 equals to element 2 stack dot append, 1, else stack dot append 0 and return true. Save it. And one more function we need, which is op verify, which takes stack as an input. And again we are checking the same thing. If length of the stack is less than 1, so that means there is nothing to do, and return false. If there is something on the stack, then get the last element from the stack, stack.pop, and if element is equals to 0, which means the last operation was not success, because in order, if this operation is successful, we will always have 1 on operation is successful, we will always have 1 on the stack. If we have 0, that means operation failed. So return false. If it is not equals to 0, that means our operation was successful, and return true. And now we can use these functions here. Simply do return op equal stack and op verify stack. Save it. Now one last function that we need to implement is check signature, and this is the main function where we'll verify the signatures. So let's define this function. op underscore check sig, and this takes tag as an input, and z, which is our signature hash. So we need at least 2 elements on the stack to perform this operation. So let's verify the length on the stack. If length on the stack is less than 2, then return false, which means we don't have the required elements on the stack. Return false. If we have the elements, then the first element on the stack is our public key. So let's fetch it from the stack by using the pop operation. And the second one is our der signature. Signature equals to stack dot pop, and we are excluding the last part from the signature. If you recall, we added the hash type. So let's go back and see that here when we signed our input, we added the sig all hash type, which is of 1 byte here. So in order to perform this operation, we don't need this, we just need the signature, so we are leaving it out of it. And we have the signature here, and now we need to import the main functions from the elliptic curve to verify the signature. So let's go ahead and import them. And the first one is, let's do import here from blockchain dot backend dot core dot elliptic curve import SHA-256 point and signature. Save them. Go back to our function. Here, do this in try and accept block, and do point equals to SHA-256 point. dot parse and parse our public key scc underscore public key and also parse our signature. So signature equals to signature dot parse and parse our signature der underscore signature. And if there are any errors, so accept exception as E and return false. So let's do if point dot verify. Verify is the function inside SHA-250. So the signature, if it is valid, we will add 1 to the stack, append 1 and return true. And if signature is not valid, add 0 on the stack dot append and return false. And that's pretty much about the check signature function. So we have all the functions ready. There is still one error I can see, so let's see what that error is. Okay, so it's not underscore, so let's change it to check signature and save. Okay, now we don't have any error here. And now let's go back to our script module and implement the evaluate function. This whole implementation is to verify the pay to public key hash. There are many other type of signatures that we have, like pay to script hash, SegWit, and many more. But since we are using the pay to public key hash, so that's the reason we have implemented the functionality just for pay to public key hash verification. But most of the things are the same in the actual Bitcoin network. Okay, now let's implement the logic to push the items on the stack and run the operations to verify the signature. Do commands equals to self dot cmd and return everything that we have. Create new list stack which is empty, and do while length of commands is greater than 0. cmd equals to cmds dot pop 0. So it will fetch the first opcode, which is this one from the stack, which is 118, and we are checking the type. If type of the command is int, so that means it's a opcode. And if you remember, we already have stored all the function definitions inside this. So now we can import this from op.py. So let's do from blockchain dot backend dot elliptic dot core dot elliptic curve import. Well, it's not inside the elliptic curve. op import this, save it, and come back to our evaluate function, and let's fetch the operation based on the command number. Operations equals to op underscore code and So we know the first operation is 118, which is to duplicate the element whatever is there on the stack, and 118 has the corresponding function definition here. So we will have this function to run. So now go back to stack. So all the functions will work like this, and let's do the last thing. If it is not an integer, then we should simply add it in the stack, which means it's a data element. So do else stack dot append cmd. So if you look at our script, so we have the opcodes and the data elements, and if it is a data element, then directly add it on the stack. But if it is a numeric or the opcode, then we need to run some kind of operations that we have already defined under op_pi. And next step is run those operations here. But there is something special about the check signature function, so we need to handle that little differently. So do if cmd equals to 172, if not operation which takes stack and z as an input. So if there is any error, then print it. Error in signature verification and return false. If it is any other operation which takes just stack as input, then we don't have to do anything. Then simply copy and run this here and remove z from the parameters. Let's add one more space here, and that's pretty much, we are done with this. Now let's understand what exactly we did here. Go back to your transaction module, and we are adding our script signature with our script public key, which means we have two more data elements. First one is our public key, and the second one is our signature, and plus the script public key with the opcodes. So which means we will have the three data elements and these opcodes to verify the signature. Don't worry if you have not understood everything about signature verification. It will make more sense once we will debug the code. I'll show you each and every element, how it works, and how the signature verification and the transaction signing works. And one last thing, if everything is okay, so we need to return true. So let's implement it, return true, and save it. And that's pretty much with the evaluate function. In the next video session, we will learn how to create the mempool, where we can push the transactions and miner will pick up the transaction from mempool and add it in a block. What is memory pool? Memory pool is a place where your verified transactions are waiting for its turn to get included in a block by a miner. So let's create a dictionary that can be shared between different processes. So copy this line and give it a name as memory pool, mempool, and then share this dictionary in our front end, so that when a user will create a transaction, that will be signed and verified, and then it will be included in the memory pool. And from that memory pool, our blockchain class will read the data, which is the miner, and then it will include those transactions in the block. So let's pass this in the blockchain as well, and in the init function receive this memory pool and create self.mempool. Self.mempool equals to mempool. We'll come back to this, and now let's go back to our run.py module and create a global variable mempool global mempool, and also receive this parameter here, mempool, and assign this value mempool equals to mempool. Let's give the name with different, so change this to caps mempool and replace it with mempool. Save it. This is the place where we will add the transactions in the memory pool, but before we do that we need to make a couple of changes. The first change we need to make is in the send.btc module. So go to send.btc. So we have not created the transaction ID here, so let's add the transaction ID. self.txObject.txID equals to self.txObject, and call the ID function from the transaction module. Save it. And one last thing, instead of returning the true flag here, return the transaction object itself. So copy this and save. Until this step we already know that our transaction has been signed and it has the transaction signature inside the transaction input. So let's change this. Receive your transaction object here. So do tx object and remove the message, and also remove this colon, remove this space as well, and save it. First check if your transaction is a valid transaction. Do if not, tx object, change the message to invalid transaction, and second, check for instance. If is instance tx object comma tx, if it is a transaction object. So first import the transaction class here from blockchain dot backend dot core dot tx, import tx, save it. So the next step is we need to verify the transaction. So how do we verify? So let's do for loop index transaction in enumerate tx object, and we need to verify the transaction input because that's where the signatures are. tx ins and do if not tx object dot verify dot input. So that's the function we have defined inside the transaction class, and it takes index as an input and script public key as an input. Script public key. So how do we get this script public key? If you remember, we have the script public key function inside the sendBTC. So we just need to pass the public address here and it will give us the script public key. So we can call this function here. So let's do it. So call this function script public key equals to send coin dot script public key, and pass your public address here, which is from address. Save it, and now we have the script public key. And if there is any issue in the transaction verification, so we should set the flag to false. Verified equals to false, and by default this flag will be always true. So let's set it to true here. Verified equals to true. Let's add a space here. So let's understand what exactly we did here. So there can be multiple transaction inputs. So we need to ensure that all the transaction inputs are valid before we can add them in the memory pool. For example, if there are two transaction inputs, the first transaction input is valid, so it's okay. But if there is an issue with the second transaction input, and it will set the verified flag to why, because then our whole transaction is invalid. So we need to ensure that all the transaction inputs are valid before we add them in the memory pool. So if everything is fine, so check for this flag. If verified mempool tx object dot txid equals to tx object. So add your transaction inside the memory pool and set the message to transaction added in memory pool and save. Okay, so this is the time to debug our code and see how transaction is signed and verified. So let's go ahead and set the breakpoint here in the run module and go to blockchain and start debug. Okay, let it start, and let me open up the browser. Okay, our front end is started. So let me okay, so let's create a transaction from this address to this address. Try sending 10 bitcoins and send. Okay, so it has stopped at our breakpoint. Let's go inside the prepare transaction function and let's see what's happening there. Go inside the prepare transaction input. Okay, so empty list is created, total is set to 0, and we are creating the script public key, and we are getting the public key hash. So here we are converting our shared UTXO into local UTXO by using the dict keyword, and let's go ahead and do that. So it will convert it into new UTXO. We would be able to see the UTXO. So these are all unspent transactions. You can see it is continuously mining and it is adding the unspent transactions into UTXO, and we have already shared this UTXO with our run module, and you can see that in our blockchain file. So we transferred our UTXOs here, right here, and now it is able to share the data between, even though it is running in a separate process, and that's why we use the multiprocessing. It is possible that if this dictionary is in use, so it may not be able to convert it, so it should wait for 2 seconds and then retry. So let's jump to the next step. So now read the data from our new UTXO. So we transferred 10 bitcoins. Here it is checking that if those transactions are locked to our public key hash. If they are locked, so it will go inside the loop and it will add the total, and total is, I think it's 50 bitcoins, and we just transferred 10, so it has created the transaction ID, and now it will create the transaction input object here and append it in the list. And again it will check if the total is less than the amount that we are transferring, then it will go inside the loop. But I think we just transferred 10 bitcoins and we already have the 50 bitcoins, so we don't need to further check any other transactions. So it should come out of the loop if balance is enough, true. This condition is also okay, and then it will return the transaction input list, and it will check this flag. So it should go inside the loop only if we have the enough balance. In this case we have the enough balance. And now prepare the transaction output to whom we are sending the coins. It should log the bitcoins to the person's public key hash to whom we are sending the coins, and go inside this. Okay, so we are getting the public key hash. So we have the script public key here, and the coins are locked to this public key hash, and these are the opcodes when we will verify the transaction input. So create the transaction output object, amount, and the script public key. And this is the fee that we are transferring. We are paying 1 Bitcoin. And then finally we are sending the change amount back to ourselves and creating another transaction output object and appending it in the list. And now we have 2 transaction outputs. So let's look at this, and you can see we have 2 transactions. First we are sending to the person, second the change amounts we are sending back to ourselves. And now let's create the transaction. So we have the transaction, and now it will create the transaction ID, and this is the time to sign our transaction. So let's sign, get our private key. We have the private key. It fetched the private key from the file, the account file, and here it is creating the object for our private key. And we are calling the input object function, sign input. Let's go inside this function, and we are creating the Z, which is our script signature, and it should create the signature, and we have it. So let's see the value of Z. So this is the numeric value. Then we are creating the signature, DER signature, and then the final signature by adding the hash type, which is sig hash all. And this is our final signature, and this is our public key, which we are creating from the private key. And finally we are adding the signature inside our transaction input that we are signing. So it has the signature and the public key, and with that we have signed the transaction. If there are multiple transactions, so it will sign all those transactions in a loop. So I think we have only one, and that's it. Now it is returning the transaction object. So let's go back, and we have the transaction object here, and you will see inside the transaction input we should have the script signature now. And there are 2 elements. The first one is the signature, and second one is our public key. Alright, so let's verify our transaction now. Okay, so we are checking if it is, the object type is transaction, and let's verify the transaction. So we are telling that for which index input we are verifying it, and we are passing the script public key to verify the transaction. So let's go inside the verify input. It is getting the object, and here it is getting the Z. Okay, we have Z, which is similar to the one when we noticed that when we signed the transaction. And here we are combining the script signature and the script public key, and then we are finally evaluating our signature. So let's go inside this, and let's see the commands that we have. So we have all these commands. So first one is the signature, this is the public key, and then these are the operation codes. We will see it in action now. And then this is the script public key hash, and then these are opcodes as well. So let's see. First it will pop the first element from the stack, and let's see which one is that. That is signature, and its type is not input, so it should add and go inside the else and add it on the stack. Right now stack must be empty, so it is empty, and let's see it now. And we have the first element on the stack, which is the script signature. Now the second element is as well the public key hash. Let's see it. Yeah, that's the public key hash, and it will add that as well on the stack. It's not the public key hash, but it's the public key itself, so it will add that on the stack as well. And the next element is opcode, which is 118, and now it should go inside this loop. It will fetch the function definition from this function. You can see that it has the function object here, op dupe for 118. So now we will have the definition of this function, and let's go inside the operation. Yeah, I see one error here. Actually, it should be else if, not if. And let's go inside it. Now it should duplicate the element from the stack. So right now we have 2 elements on the stack, so it will duplicate the last element from the stack. And let's do it. And it is fetching the last element and adding it back to stack by append statement. So let's do that. And now we have, I see, okay, so another error that we noticed, it should have returned true from there, and I see in the op underscore dupe we did not return true, and that's the reason it is going inside this error loop. So let's fix both the issues. The first one, we need to add else if here, and the second one, inside the op underscore dupe we need to return true. So let's return true from here. Return true, and also add else if here. And save it. Let's end the script and run it again. Blockchain, run and debug. Let's bring up our front end again. Okay, so let's transfer it again from the same address to this address, and this time let's transfer 100 coins or 90 coins. So we should have 2 transaction inputs now. So it is already here, so I'm not gonna run through everything again, so we'll directly go to the error where we face the error. So transaction, okay, transaction object is prepared. Let's see the transaction inputs we have this time, and you can see we have 2 transaction inputs this time because we transferred 90, and the maximum bitcoins in one transaction is only 50. So that's the reason we have 2 transactions, and both should have the script signatures. I can see it here, it has the script signature, and the transaction 2 should also have the script signature, and I can see it here. So both has the script signature. Now let's directly verify the transaction, and let's verify the first transaction first, index 0 and script public key this. Let's go inside the verify input, skip all this, we have already seen that. Go directly inside the evaluate function, and first signatures were added, and then the script public key is added, and we have the operation now to duplicate it, and now it should not go inside the error. And perfect, it didn't go inside the error. And the next is, let's see what is there in the command. 169, again it's the op code, so that means we need to perform some kind of action here. So let's see what is op code. So it's hash 160, so we need to perform the hash. So let's see, go inside the function, and it is popping the element from the stack, and it will run the hash 160 on this and append it on the stack and return true. So now let's see what we have it on the stack. So we have this element on the stack, and let's see what is the next element. So this is the public key hash, so it should add it on the stack. Okay, and the next is the op code, which is equal verify, so it will verify the hash. So let's go inside and see what exactly it is doing here. Equal verify, let's go inside the op equal first. It is checking if there are at least 2 elements on the stack, and it is popping up the first element and the second element, and then it is comparing both the elements. If both the elements are same, then it is a success and it will append 1 on the stack. and it has appended 1, return true, and second one is equal verify. So let's verify that. It is checking if the element on the stack is 1. If it is 1, then fine, that we have verified successfully, otherwise it should return false if it is 0. Okay, equal verify is done. And let's see the next operation. The next operation is check signature, and this is the main signature to verify the signature, and we are passing the stack and Z, which is our signature hash. So go inside it. So first it is fetching the public key, then signature. It is excluding the last element of the signature because which is the signature hash type, and we don't need it when evaluating the signature. Go inside this, and it is passing the public key and then signature, and finally it is verifying the signature. If signature is verified, it will append 1 on the stack. So hopefully it will verify, and yes, it verified the signature, so that means our transaction is good, and return true. And it will do the same thing for the second transaction that we have 2 transactions here. So let's do it directly. Run the verify input function, and yes, it has verified the second transaction as well because it did not go inside the loop. So that means both the transactions are verified, and now it will add the transaction in our memory pool. And cool, so our transaction is verified successfully. Now it should display the message on the front end, and let's see it. And we can see the message here, transaction added in memory pool. In the next session, we will see how to read those transactions from the memory pool and add them in the block. In our previous video, we saw how to add the transaction in a memory pool, and this memory pool is shared between the front end and our blockchain file. So as soon as the transaction is added in the memory pool, so it will be available for the miner to read and include it in a block. So in this video, we will see how to add the transaction in a block. So first, let's create a new function here. So create a function called read transaction from memory pool. And create a list. First, create transaction IDs. So we are creating an empty list to store all the transaction IDs here, and it will be helpful when we'll create our Merkle root. So the next step is create another list, add transactions in block. So here we will collect all the transactions from our memory pool, and then we will add them in a block. So read the transactions from the memory pool for tx in self dot mempool self dot tx ids dot append. So for each transaction, collect the transaction ID, and then self dot add transactions in block dot append. Read the transaction from memory pool and add. And that's pretty much about this function. So let's add a little documentation here. Read transactions from memory pool. Save it, and in the next step, go back to your add block function, and here we will add our transactions. So we have a Coinbase transaction as well, so we need to add the Coinbase transaction in our transaction list that we have prepared. So let's add the transaction ID first and then the transaction itself. So after this step, self dot tx ids dot insert 0 Coinbase transaction dot tx id. As per Bitcoin consensus rule, your Coinbase transaction should be the first transaction in every block. So that's the reason we are setting it 0 here. And add the transaction as well, self dot add transaction dot insert 0 Coinbase transaction and save it. We'll come back to the Merkle root. For now, let's leave it as it is. When we'll create the Merkle root, then we'll make this change here. For now, just leave it. And the next step is we need to convert our transactions into JSON format, because right now these transactions are in byte format, so we need to take care of it. So let's create a new function, convert to JSON self, and create a new list, self dot tx JSON empty list, and for transaction in self dot add transaction, read every transaction from the add transaction list and convert it into JSON format, self dot JSON dot append, and do tx dot to dictionary. So we already have this function defined inside the transaction module. However, we need to make some changes in this function. We'll see how to do that. And once everything is converted, we will simply replace this Coinbase to this list. So let's copy this and remove it from here, paste it, save it, and call this function after the UTXO store, self dot and save. Now let's go back to the transaction module and make the changes in toDictionary function. So the first thing is we are not just converting the Coinbase transaction now, so we are converting all the transactions. So let's remove this and make it more generic, and do for loop here. Now there can be multiple transactions, so we need to convert all the transactions. So for tx index transaction input in enumerate self dot tx underscore ins, and if self dot is Coinbase transaction. In Coinbase transaction, we store the block height, which is in little endian. So we need to convert that into integer. So let's do that. Do tx in script signature dot cmds, and we store it at the first place in the command, and do little endian to int tx underscore in dot script signature dot cmds 0, and save it. And next step is convert the previous transaction hash dot previous tx in dot previous transaction. Simply use the hex method to convert it into the string format. And the next step is run a for loop for index cmd in enumerate. Now we need to convert the script signature if there are any bytes in the script signature, so convert it into hexadecimal. Script signature, CMDs, and this is eligible for the normal transactions. For normal transactions, we have the script signature, we have the script public key, so we need to convert everything into hexadecimal format. Do if is instance CMD. So we are simply checking if there are any bytes, then convert it into hexadecimal. txin dot script signature dot cmds and index cmd dot hex. Save it. So it will convert everything in hexadecimal format. And the next step is convert tx in dot script underscore signature equals to tx in script signature Since script signature is the object itself, so we need to convert that in dictionary and save it. And last, convert the transaction input object into dictionary. tx index equals to txin dot dictionary. Save it, and we can remove this entirely now. And we need to modify the transaction output as well, so let's remove everything from here. Now we can have multiple transaction outputs as well, so we need to run the for loop here as well. Index tx out in enumerate self dot tx outs tx out dot script public key dot cmd. We know that here we have the bytes only at the second place in the command, which is our public key hash, so we are just converting that. tx out dot script public key dot cmds to dot hex. And now convert the script object into dictionary. tx out dot script dot public key equals to tx out dot script public key dot dictionary. So this will convert the object into dictionary, and we can easily save it in JSON. And the last is convert the tx out object itself in dictionary. tx outs index and tx out dot dictionary. Save it, and I think we are done with everything. Go back to blockchain module and let's check if everything is done. So we need to call this function here. So the first thing is we need to read the transaction from the memory pool. So let's call it in the first step itself and save it. And let's quickly debug it, remove all the breakpoints and set the breakpoint here and debug. For now, we know that we have nothing in the memory pool, but let's run this. Okay. Next step, keep going and add the transaction. Right now the transaction IDs are blank, and now it will add the Coinbase transaction ID here. and we have the transaction ID here. And next, the add transaction list is blank for now. You can see it here. Now it will add the Coinbase transaction as a first transaction. And let's see it quickly. Yeah, we have the transaction object here, and we'll take care of the Merkle root in the next video. For now, let's continue and mine the block. Meanwhile, let me bring up the front end as well, and we will transfer the coins from this address to this address once we have the UTXO available in self.utxo. Alright, to store the UTXO here, next step, and convert to JSON now. So let's go inside this and see what's going on. Read the first transaction, and it should convert it into dictionary. Let's go inside dictionary. Okay, it is a Coinbase transaction. That's good. Okay, so we have some kind of error here. So it's a typo error. It should be CMDs, not CMD. So let's quickly fix it. And let's run it again. Let's quickly skip everything that we have already seen. Mine. Okay, go to convert function directly, and hopefully it will work now. All right. Okay, it has converted everything. So let's quickly look at the object JSON, and it has converted everything into dictionary. We do not have any object now, and now I should be able to write this into JSON without any issue. So let's run this, and that's nice, it worked. Now let's transfer some coins, and transfer 10 coins. Okay, so now we should have the transaction in the memory pool. So let's go inside and see. We should have a transaction now, and yes, we do. And it will add the transaction in add transaction. Right now it should be blank, and you can see it's blank. And now we have one transaction here. So let's look at this. So we should have the transaction where we send the 10 bitcoins. Let's look at the amount in the transaction out. And yeah, that's the one. We are transferring 10 bitcoins here, and this is the change transaction where we are sending the money back to ourselves, and that's good. Let's quickly mine the block now, and here we are adding the Coinbase transaction as well as our first transaction, because as per the consensus rule, your Coinbase transaction should be the first transaction, and first we are adding the transaction ID and then the transaction itself. So let's do that. Mine the block. Okay, store it into UTXO, convert it into JSON, and it has converted everything. Now write it into our file, and perfect, everything is working fine. In our next video, we will see how to create the Merkle root. In this session, we are going to learn what is Merkle root and how to create it. But before we jump into coding, let's understand what is Merkle root. So we know that each transaction has the transaction ID. For example, on my screen, I have 4 transaction IDs, 1, 2, 3, and 4. So Merkle root, it will combine the hashes together. For example, it will combine the transaction ID 1, transaction ID 2, and it will create a new hash. Then it will combine the transaction ID 3 and transaction ID 4, and it will create a hash 1. Finally, it will combine these two hashes together, and this is our Merkle root. So what if we have odd number of hashes? If in case we have the odd number of hashes, then it will duplicate the last hash, and then we will have the even number, and the same process continues, and eventually we'll have the final Merkle root. So to create the Merkle root, let's go back to the util module, and inside util, go to util.py and create a new function here, Merkle root, and it takes hashes. And let's add the documentation. Takes a list of binary hashes and returns the Merkle root, and do current level equals to hashes while length current level is greater than 1. So we know that Merkle root is the final hash, so we need to continue the loop until we have the final hash. So do current level equals to, we need to create one more function, so let's name it as Merkle parent level, Merkle parent level, and pass current level as an input. And let's create that function here, Merkle parent level, and hashes as an input. So let's document it here. Takes a list of binary hashes and returns a list that is half of the length. I'm sure from the documentation it is clear what exactly we are going to do here. So do if length of hashes if it is an odd number, then append the last hash, hashes dot append hashes -1. So it will duplicate the last hash. And next, parent level equals to blank, and do for I in range start from 0, length of the hashes, and jump by 2, and define parent equal to run hash 256 and hashes I and I plus 1. So it will start from 0 and 1, then 2 and 3, and so on. Then parent underscore level append the parent, and whatever hashes are passed, it will do the exact half of it and return parent level. Save it, and finally we will return current level. Now let's import the Merkle root function here. Merkle root, and let's call it here. Replace this Merkle root, and if you remember, we already have all the transaction hashes, so pass this as an input, save it. But one more thing that we need to take care is the Merkle root function will take bytes as an input, and we need to convert it here. So do bytes from hex and tx, and same do it here. Bytes from hex Coinbase transaction hash, and it is returning the whole list here. So instead of returning the list, let's just return the last element. Also, there should not be a comma here because we are concatenating the hashes, so it should be plus here. Save it, and then to reverse the hash and do hex, and then we will have our Merkle root. Let's quickly debug and see if everything is working fine. Set the breakpoint here, run and debug. Okay, so let's see. Okay, so it is working fine. So we have the Merkle root. Now we will create one transaction, and it should combine the two hashes together, and then we will know that everything is working fine. So let me quickly create one transaction. So let me set the breakpoint here and jump to that read transaction function. And now let me go back to the browser, create a transaction. If you remember, our unspent transactions are stored in cache memory. So when we turn off our mining node, so it will wipe out everything. In actual Bitcoin node, if mining node goes down, so they will request the data from other active nodes, and then they will prepare the unspent transaction list from the blockchain. But in this case, we are just running one node, so we cannot request the data from any other node. But in our premium course, we will run our multiple mining nodes, and when we shut down one node, that node will request the data from other active nodes, and it will prepare the unspent transaction list first, and then it will start validating the transactions which are there in the memory pool. Let's read the transaction from the memory pool. Now we should have the transaction here, so we can see it in the add transaction. So we have the transaction here, and let's do this, jump to this, add the Coinbase transaction. Now we have at least two transactions. Yeah, we have the two transactions. Now it will create the Merkle root. Let's go inside the Merkle root. We have two transactions. It will go inside the Merkle parent level. It's an even number, so it won't go inside this. Now it will create the hash. It will combine two transaction IDs together, and then it will run hash 256 on top of that, and we will have the Merkle root. And we have the parent, which is our Merkle parent. It will append, and in Merkle parent we have only one hash, which is the final one. So now our condition is satisfied. It will come out of the loop, and it will return the hash. And here it reversed that hash and calculated the hexadecimal value, and this is the final hexadecimal value. In our next video, we will see how to remove the spent transaction from the UTXOs, and also we will implement the fee functionality where miner will claim the fee for adding the transactions in a block. In this session, we will learn how to remove the spent transactions from the UTXO and also add the new transactions in the UTXO. So now that we have the memory pool functionality up and running, so that means we are creating new transactions. So those transactions should go inside the unspent transactions, and at the same time we need to remove the transactions that we are using. So let's go ahead and implement the functionality. First, remove this Coinbase, because until this step we were just adding the Coinbase transaction. So remove this and update this function. Okay, so remove this step as well. Run a for loop for tx in self.add transaction. So in add transaction we have all the new transactions, which means those are unspent transactions, and move this inside the for loop and update tx id and the transaction itself, tx, save it. And the next step is we need to implement the function to remove the transactions that are already been used. So define remove spent transactions self pass. So first let's prepare this list from where we will read the data, what all transactions we need to remove. So we are already reading the data from the memory pool, so we just need to add one more list here. So add self dot remove spent transactions, set it to empty, and here create a for loop here for spent in self dot mempool. So we are reading the transaction from memory pool, and then we are just concerned about transaction inputs. So read the transaction input. Now here we will add the previous transaction hash and the previous transaction index in the remove spent transaction list that we just created. So do self dot remove transactions dot append and create a list, and inside the list we will do spent dot previous transaction hash comma spent dot previous transaction index, and based on these two fields we will remove the transactions that are already been spent. Go back to remove spent transaction function and implement the logic to remove the transactions. Open a for loop for tx id and index in self dot remove underscore spent transactions. So we have stored the previous transaction hash and the transaction index, so we are reading it here, and do if tx id underscore index 0th index, which is our previous transaction hash, convert it into hex and check if it is there in self.utxos. If length self.utxos and txid index 0. So basically this is the transaction hash, and we are checking if the transaction outputs are less than 2, then we can straight away delete the transaction. And do del self.utxos txid index 0.hex. For example, if we are using the Coinbase transaction and we know that in Coinbase transaction we are transferring the amount to just one person, but if it is a regular transaction, so then transaction output could be two: first to the person whom you are sending the coins, and second your change transaction. So if it is a Coinbase transaction, then we can simply delete it if we have spent. And the second is, if it is a normal transaction, do previous transaction equals to self.utxos txid index previous transaction hash, convert it into hexadecimal, and self dot UTXOs, TX index 0 X equals to previous transaction output outs dot pop the index that we have already spent, tx id index 1. First let's fix this. This was supposed to be transaction id and index, so do control D, select everything that you want to change and do tx id underscore index, and it will change it in all the places. Save it. So first let's understand what exactly we did here. If in case there is only one transaction output that we have already spent, so we can straight away clean or delete the entire transaction. But if in case there are more than two transaction outputs, miner will only delete the transaction output that has been spent, and he will keep the other one for the future reference, because it's possible that the other person may use that transaction in future. Okay, now let's quickly test if everything is working fine. So first thing, add a print statement here. Transaction added, add the transaction ID. We are adding the print statement so that we can visualize what transaction was added and which one was deleted. Copy this, paste it here as well, and do spent transaction removed, and update the transaction ID to this. Save it. Okay, let's fix the alignment. Save, and also call this function right here, self dot, and remove all the breakpoints. Set the breakpoint right here, run and debug. Click on continue. Mining has started. Okay, so block is mined and we can see this transaction ID has been added. So this is our Coinbase transaction. Now let's transfer coins to someone else by using this Coinbase transaction from this account to this account, and let's transfer 10 bitcoins. Okay, so now transaction is there in a memory pool. Continue, and I'll click on continue. Okay, mining is going on. All right, so we can see it here. It did use this transaction, and after using the transaction, it has removed it. Spent transaction removed. Right? It was the Coinbase transaction, so there was no other transaction output. There was only one transaction output which we have already used. So we have removed the entire transaction. This is the second transaction, which is the Coinbase transaction for this block, and this is the transaction where we transferred the 10 bitcoins to the other address, right? And in the same transaction we have the change as well, where we have transferred the money back to our address. I hope it is clear now. We have read the transactions from memory pool and added them in a block, but we did not remove them from the memory pool. So let's go ahead and take care of this functionality. So once transactions are added in a block, let's remove them from the memory pool. So create a new function, define remove transactions from memory pool, self, and add a documentation. Remove transactions from memory pool, and add a space here, And it's very simple to remove the transactions from the memory pool. We already have the list of transactions that are there in the memory pool that are added in this self.tx IDs. So we simply need to read and remove. So let's do for tx in self.tx IDs. If tx, convert it in hex because the values in the tx IDs is in byte format. So do self dot mempool and delete self dot mempool and do tx dot hex, and that's it. It should delete it from the memory pool now. Let's see what's wrong here. Okay, it's not def but del. Save it and call this function inside the add block. Call it after here, self dot save it, and that's it. We have implemented the functionality to remove the transactions from memory pool. Next topic is calculate fee and claim it in a Coinbase transaction. So let's go ahead and define a new function called calculate fee. Calculate fee self, define variable self, input amount, and self dot output amount. And the difference of input minus output will be our fee. So this means how much money the sender has and how much he is sending out. Let's say miner has 10 bitcoins in his wallet. He is sending 5 bitcoins to somebody else and 4 bitcoins back to himself as a change. So the remaining 1 bitcoin will go to miner as a fee so that he can include the transaction in a block. Let's implement the logic to calculate the fee. First calculate input amount, for tx id underscore index in self dot remove spend transactions. If you remember, we have already collected the transactions that we need to remove from the UTXO. So we have the transaction ID that we can use to fetch the transaction amount, because your transaction amount is there in the transaction output. So let's go ahead and retrieve the transaction output here. So do if tx id index, and at 0th position we have the previous transaction hash, convert it into hex in self dot utxos, and do self dot input amount plus equals to self dot utxos and your previous transaction ID 0.x and tx out, which means our transaction outputs, and at which index the transaction that we are using. So add the index number and then fetch the amount that we have associated with that index amount, and that's it. It will fetch the transaction input amount. And now let's implement the transaction output amount. Calculate output amount. Calculating the transaction output amount is very simple. Let's implement the for loop for tx in self dot add transactions. So we already have the list of transactions. For tx out in tx dot tx underscore outs. So we are reading the transaction outputs only. Self dot output amount plus equals to tx out dot amount. Now we have the input and output as well. Now simply do self.fee equals to self.input amount minus self.output amount, and that's our fee. Now let's call this function right here. Self.calculate fee. And now we need to add this calculate fee in the Coinbase transaction. So once we have the Coinbase object, we can simply change the transaction amount. So let's do it. Coinbase transaction dot tx outs. First element in the list dot amount equals to Coinbase transaction dot tx outs 0th and amount plus whatever fee we have collected, add it. Now we have changed the Coinbase transaction, so which means we need to update our transaction ID as well. So instead of using the tx ID here, call the ID function. It will calculate the new ID based on the changes we have made to this transaction. And that's pretty much, we are done with it. Save it and let's quickly see if everything is working fine. Set the breakpoint here on the calculate transaction and run and debug. Okay, that's good. Everything is working fine, but we need to see if it is calculating the fee correctly. So for that we need to transfer some money. So let's do that. Transfer coins from this address to this address, and let's say we are transferring 10 coins. And let's complete this cycle. And then we will press the send button once we have the UTXO to spend. And now we have it. Click send. And I'll run the cycle once again. Now it should read our transaction from the memory pool, and let's go inside the calculate fee function. Okay, so let's see the input amount. So we have 50 bitcoins which are there in the Coinbase transaction, so that's good. Let's see the transaction output now. So we have two transactions in the transaction output. First, the 10 coins we sent to the person, and then the remaining change to back ourselves. And let's see the difference. We have fee 1 Bitcoin and the total input was 50 and the total output is 49 Bitcoins. So which is perfectly in sync. Let's see our Coinbase transaction now. And the Coinbase transaction ID is this one right now, and it will update the ID once we'll add the amount here. Let's see the current amount of the Coinbase transaction, which will be in the output. Right now it's 50 Bitcoin. So now it should be 51 after running this statement. Let's see. And yeah, we have 51 Bitcoins now. So that means we have included the fee. Now we are updating the transaction ID here. And awesome, everything is working fine. So we have implemented the fee functionality as well. Next topic is difficulty. Difficulty is a number that regulates how long it takes for a miner to add new block of transactions to the blockchain. This difficulty value updates every 2 weeks to ensure it takes 10 minutes to add a block to the blockchain in official Bitcoin blockchain. Define a variable initial target. Set it to this number. This is a number, but you see it in hexadecimal form. So let me quickly show you this number. Paste this copied value, and you can see this is a numeric value. So this is the value against which our block hash is compared, and once block hash is below this value, so that means we have mined the block. So let me close the terminal. Initialize the variable self dot current target and assign the value of initial target here. Create one more variable self dot bits, and this bits variable will hold the same target but in short form, because there is a space constraint on the Bitcoin blockchain. So Bitcoin developers found a way to convert the same numeric value in a short form. So we need to create one more function, target to bits, and pass initial target. And let's go ahead and define this function here inside the util. This function will convert the initial target value in a shorter form. So let's go back to our blockchain and import this function here, target to bits. Go to block header class right here and change it to self.bits, the value that we just set, self.bits. And now we can remove this and also set the target to self.current. Let's go inside the block header class, receive the target value that we just passed, target, and do self.block hash equals to target plus 1. We are deliberately setting the block hash value greater than the target so that it should go inside the loop and try to find the value of block hash which is below the target. So now let's replace this with self.block hash greater than target. So it should continue this loop until the block hash is greater than the target. Now we need to make some changes here. Now let's replace this piece of code with this one. And let's import all these functions here. Little endian to int and int to little endian. So this is nothing new. We have done this multiple times. So we are just concatenating all the values together. First we have converted all the values in byte form. Then we have concatenated everything together. Then we ran the hash 256 function on those values. And finally we are converting it into integer format so that we can compare it against the target value. And the last thing is, let's do self.block hash equals to int to little endian. Right now the block hash is in numeric form, so we need to convert it into hexadecimal form so that we can store it in JSON file. So do self.block hash, it is of 32 bytes, convert it in hex and then reverse it, save it. And the last thing, we need to convert the bits in hex value as well, because right now bits is in byte format. Bits, and it's simple, do self.bits and hex. And that's pretty much with this function. This is the right way of implementing the mine function, and this is how exactly Bitcoin is comparing your target with the block hash. The 4 leading zeros is just the simplest form of representation how mining works. Now let's go back to blockchain. Let me clear my blockchain file and we will do a fresh start. Blockchain, remove everything, save it, and now let me start my blockchain. And perfect, it has started mining. We have block 1, block 2, block 3. Now let's look at the data. And let's look at this block. And we can see the previous block hash is starting with 0. The new block hash is starting with 4 zeros. So everything is working fine. And we also have the bits here, the target difficulty. And with this, we have changed everything that we had to inside the block header class. We have changed our mine function. Instead of comparing the 4 leading zeros, we have implemented the actual core concept of Bitcoin blockchain inside our blockchain. So we are comparing the block hash with the target value. If block hash is below the target value, that means we have successfully mined the block. There is one last thing that we need to take care. So we have the block size. Until now, we were passing the block size 1 here. So let's calculate the block size and pass the actual value of the block size. So block size is comprised of your block header size plus the transactions. So block header has version, previous block hash, Merkle root, timestamp, bits, and nonce value. So version is of 4 bytes, previous block hash is 32 bytes, Merkle root 32 bytes, timestamp 4 bytes, bits 4 bytes, and nonce 4 bytes. So by adding all these values, so block header is of total 80 bytes. So let's declare the block size variable. So declare it here, self dot block size, and set it to 80. And in the next step, we will add the transaction size. So let's do that. Self dot block size plus equals to, pick up this transaction, do length, serialize the transaction, block size is in bytes, so we are serializing the whole transaction, so it will give us the total size in bytes, and then we are adding the each transaction size in the block size. It will run in loop, so whatever transactions are coming in memory pool, it will calculate the size of each transaction, add it in the block size. Now copy this, and if you remember, in this step we have not included the Coinbase transaction, so we need to add the Coinbase transaction right here. So once we have created the Coinbase transaction, do self.block size plus equals to length and serialize the Coinbase transaction. Alright, so we are done with this. Now copy this and replace this one with the actual block size. And let's remove all the breakpoints and quickly run if everything is working fine. So set the breakpoint here. So right now block size is 80 because we know the block header is of fixed 80 size, and now it should add the Coinbase transaction size in this block size. And yeah, we have 167, which means 87 bytes is the Coinbase transaction size. So let's write it in the file. And perfect, it is working fine. So let's quickly publish one transaction and we will see it is picking up the block size from memory pool as well. Let's transfer from this account to this account and transfer 20 bitcoins. Send. Okay, transaction is added in the memory pool. So let's go ahead and read the transaction from memory pool. So it will set the block size to 80, and now we have the total block size of 305. So it is working fine, and now it should add the Coinbase transaction size in the block size. So current block size is 305, and let's see the new block size after Coinbase transaction, 392. Perfect. So everything is working fine. This brings us to the end of the part 1 of the blockchain course. We have covered a lot about the blockchain, but there is still much more to learn. By now, you must have a solid foundation of blockchain technology. But now is the time to take your skills to the next level and become a true expert in the field. That's where the paid version of our blockchain comes in. It is the continuation of the same course. Unlike other courses, we are not charging hundreds or thousands of dollars. We know everyone cannot afford this kind of money, so we have published our course on Udemy, which everyone can afford. Our comprehensive curriculum is designed to provide you with in-depth knowledge and a practical experience that will set you apart from the rest. You will dive deeper in the inner workings of the blockchain technology, exploring topics such as how to create the peer-to-peer network, how to broadcast transactions to the other miners, how to resolve the conflict between the miners, and much more. But it's not just about the theory. Our hands-on projects and the real-world examples will give you the opportunity to apply your knowledge and build practical skills that are in high demand by the companies and the organizations around the world. With the paid version of the blockchain course, you will have access to the exclusive resources, including additional lessons, quizzes, and a dedicated community of like-minded developers. You will be able to ask your questions directly to me. Investing in the paid version of blockchain course is an investment in your future. Do not settle for just a basic understanding of blockchain technology. Take your skills to the next level and become a true expert in the field. Join us now and start your journey to become a top blockchain developer. You will find all the links in the description below. See you on the other side, and bye for now.